Hello there and welcome to Life Beyond Seen, where curiosity drifts on quiet tides and science has a soft voice. Tonight, we're leaving the ticking of clocks behind and turning instead to the slow pulse of the ocean, a place that has been alive far longer than anything that walks on land. Beneath those endless layers of blue, in the cold corridors of salt and pressure, dwell creatures that have been here since before the first trees, before the mountains wore their current names, before mammals even learned to breathe air. They are not relics exactly, not fossils turned to stone, but living pages from the oldest book on Earth. And somehow, even after millions of years of extinction and upheaval, they're still here, moving quietly through waters that remember every age that's passed. Where are you listening from tonight? Maybe somewhere far from the sea, where the air smells like earth and pine instead of salt. Or maybe you can actually hear the hush of the surf through an open window. The ocean connects us all, even if you've never touched its edge. Every breath you take carries oxygen shaped by its unseen life. Every glass of water once fell as rain after a journey through its clouds. And somewhere within it, right now, something ancient is moving. Something that watched the continents shift, the stars realign, and the first humans look out across the waves wondering what was under there. If you find this kind of slow wandering through science and story a comfortable place to rest your thoughts, I'd be ever so grateful if you liked this video and maybe subscribed. It helps this little corner of calm reach others who might need a quiet companion to drift with for a while. Now let's begin, or rather, let's sink. Because this story doesn't start on the surface, where the sunlight dances and gulls cry. It starts where the light dies, where the pressure folds time into something slow and deliberate. Down there, the clock of evolution ticks differently. It doesn't rush or panic, it waits. That patience has allowed certain creatures to remain almost unchanged for hundreds of millions of years. Not because they're stubborn, but because they were perfected early. The ocean is a museum without walls. Every current carries the DNA of survivors, creatures that saw empires rise on land and sink again without noticing. The horseshoe crab, for instance, has been crawling along sandy bottoms for more than 400 million years. It predates the dinosaurs, outlived ice ages, and watched the continents drift apart like sleepy tectonic giants. When you look at one, you're not seeing something primitive. You're seeing something that never needed to improve. Its design works, its armour, its blood, its rhythm, all still doing their job without complaint. The ocean keeps these old lives safe because it doesn't change as quickly as the land. The water shields, buffers, muffles. The temperatures shift, but not drastically. Landscapes flood and dry, but the deep stays steady. That steadiness is what allows evolution to preserve things, almost like they were pressed between pages. It's not so much that the ocean refuses change, it's that it moves with a slower heartbeat. So when the world above burns, freezes, or forgets, something beneath quietly keeps going. Think of the jellyfish, one of the most ancient life forms still drifting through every ocean. They have no brains, no bones, no blood. Just a pulse, a pattern of cells that's worked for over 500 million years. Their simplicity is not weakness, it's strategy. When everything around them changes, temperature, salinity, food, predators, they adapt not by evolving new features but by staying minimal. It's the same philosophy that keeps some of the oldest tools still useful. They never broke, so there was no reason to fix them. If you were to shrink yourself and drift among these timeless beings, you'd see the ocean as a living archive. Sharks glide past carrying genetic blueprints older than forests. Nautiluses spiral upward, wearing shells that have barely changed since the age of trilobites. Each one a reminder that survival isn't always about innovation. Sometimes it's about patience. The ocean rewards patience more than cleverness. It's strange to think that these creatures have watched our entire lineage evolve. When our ancestors crawled from the sea onto damp sand, they were already ancient. They survived 5 mass extinctions while almost everything else vanished. Imagine the kind of quiet persistence that requires. For us, a single lifetime feels long. For them, survival stretches into the incomprehensible. We call them living fossils, but that phrase misses something. It sounds static, like they've been trapped in time. In truth, they're active, vital, quietly successful. The horseshoe crab's blood, for example, has become indispensable in modern medicine. It clots instantly when it meets bacterial toxins, which means it's used to test the safety of vaccines and implants. Every sterile syringe, every clean IV drip owes something to a creature older than trees. There's a poetic irony there, though I promise not to be poetic, maybe just a small one, that the blood of an ancient survivor keeps our fragile modern lives safe. The more we study these ancient species, the more we realise that evolution doesn't always mean progress. It can also mean endurance. The word killer in our title might suggest jaws, speed, violence. But these ancient killers rule the ocean not by aggression alone. They dominate through balance. A shark doesn't destroy its ecosystem, it regulates it. Jellyfish don't chase prey, they drift into it. Even the tiniest planktonic predators, invisible to the naked eye, hunt with quiet efficiency honed by eons. What makes them remarkable isn't that they kill, but that they've survived in a world designed to end things. Extinction is normal, survival is the anomaly. And yet, here they are. When you think about the phrase ancient killer, you might picture something monstrous. Teeth, tentacles, darkness. But if you slow down and look at the ocean through evolutionary eyes, the word killer becomes something else. It's not about malice or drama. It's about mastery of a niche so complete that nothing could push you out of it. For hundreds of millions of years, sharks have patrolled the same corridors of current, their senses tuned to the faintest heartbeat miles away. They were perfected long before mammals appeared. Even when asteroids wiped out 75% of life, sharks barely flinched. Their design is not outdated, it's eternal, and every time one cuts through the water, it's a ripple from an ancient blueprint still unfolding. The ocean holds the memory of everything that's ever lived there. When light filters down through the layers, it touches particles that once belonged to creatures from the Devonian, the Cambrian, the Ordovician. Eras so far removed from our sense of time that they might as well be dreams. Yet within the DNA of these old predators, that history remains alive. Sometimes people ask why we're drawn to the ocean, why so many of us feel calm just watching waves or hearing their rhythm. Maybe it's because somewhere deep in our biology we remember it. Our blood still carries the same balance of salts as seawater. The electrical impulses that keep our hearts beating are echoes of the chemical gradients that first powered life in ancient tides. We're not just observers of the sea, we're its continuation. And when we look at these ancient creatures, we're seeing not strangers, but ancestors. It's humbling to realise that these so-called killers, sharks, jellyfish, crustaceans, cephalopods, are not villains in a natural drama, but the stewards of the ocean's equilibrium. Without them, entire ecosystems would collapse. Sharks keep prey populations healthy by weeding out the weak and sick. Jellyfish recycle nutrients. Microbes digest the remains of everything that falls. Even decay, in its own way, is a kind of caretaking. The ocean runs on death, but it does so with precision, not cruelty. As we explore further tonight, we'll meet these survivors one by one, not as monsters or curiosities, but as teachers. They've been through everything the planet could throw at them. Meteor strikes, volcanic winters, shifting continents, changing chemistry. And they're still here. Each one carries a solution to a problem we didn't even know existed yet. How to survive without light. How to hunt without sight. How to sleep without a brain. When you think about it, that's more astonishing than any fantasy creature we could imagine. The dragon, the kraken, the leviathan, all pale beside a real jellyfish that can live forever under the right conditions. That's not myth. That's Turritopsis dorni, the so-called immortal jellyfish, which can revert its cells back to a youthful state and start its life cycle again. Somewhere right now, one may be resetting itself for the 100th time, quietly defying the idea of an ending. And yet, for all their longevity, these species exist in a fragile balance. Pollution, overfishing, warming waters. These are new challenges, one's evolution never rehearsed. The ocean's patience may be vast, but it isn't infinite. What survived 5 mass extinctions may not survive us. Still, there's hope in understanding them. Every adaptation they've perfected offers clues for our own survival. From the shark's immune system, which resists disease, to the jellyfish's regenerative cells, to the nautilus's buoyancy control. Nature has already solved problems we're only beginning to face. So as you listen, let your thoughts drift a little. Imagine the deep not as a dark alien place, but as the planet's original heartbeat, the rhythm that began everything and never stopped. Somewhere below, in that slow twilight, creatures older than the word ancient move as they always have. They are the survivors of time's harshest tests, and tonight they'll be our guides. Because when we talk about ancient killers still ruling the ocean, we're really talking about life itself. Persistent, adaptable, endlessly inventive, and perhaps, in its quietest forms, immortal. And now, as we drift deeper, the light thins, the water cools, and a familiar shape glides across the sand. Its shell gleams faintly like old bronze. Its legs tick forward with patient rhythm. A creature older than the dinosaurs, older even than flowers, still walking the same paths it once shared with trilobites. The horseshoe crab is waiting. The ocean remembers everything. Not in a human way, with stories or emotions, but through layers of chemistry and life that never really leave. Every drop of seawater carries traces of the past. Dissolved bones, ancient shells, molecules from creatures that vanished long before our species existed. If you were to take a single cup of seawater and somehow read it like a text, you'd find fragments of every age written there. Calcium from coral reefs that rose and fell, iron from meteor dust that rained into prehistoric waves, carbon from plankton that lived for only a day but left their signatures in stone for eternity. The ocean doesn't forget. It recycles. Down in the dark, the boundaries between living and dead blur. When a creature dies at the surface, its body begins a slow descent known as marine snow, a soft, continuous drizzle of organic particles drifting toward the seafloor. It falls endlessly, like dust through a beam of light, except that here the light never reaches. It feeds the deep, builds sediments, and slowly turns into rock. Over millions of years, the remains of tiny organisms harden into chalk cliffs or fossil beds, which then rise up again as mountains when continents shift. Eventually, those same minerals wash back into the sea. The cycle doesn't stop. The ocean has been burying and rebirthing its own past since before complex life began. Every grain of sand on the ocean floor was once something else: a coral, a shell, a volcano's ash, a skeleton, a comet fragment. Time here isn't measured in years, but in sediments, each layer a silent page. If you could dig through it, you'd find the history of extinction written in texture and colour. A dark band might mark a volcanic winter. A sudden change in fossil types could reveal a mass die-off. A thin line rich in iridium might trace the asteroid that ended the dinosaurs. And just above that line you'd find life beginning again, quietly rebuilding itself from what was left. The ocean doesn't rush to forget disaster. It simply folds it in and moves forward. That's how the creatures that still swim there learned resilience. They are not just old, they are trained survivors, forged by countless collapses and recoveries. Some of them carry physical reminders of those ancient lessons in their bodies. The horseshoe crab, for instance, breathes with book gills, a structure that once allowed its ancestors to survive in waters thick with volcanic ash. The nautilus controls its depth with chambers filled with gas, an invention that predates trees. The shark's cartilage skeleton, so different from our bones, makes it lighter and more flexible, ideal for endurance in a changing world. It's tempting to think of evolution as progress, a march toward complexity and intelligence. But the ocean tells a different story. Sometimes simplicity is the ultimate sophistication. The jellyfish doesn't need a brain to thrive, it only needs rhythm. The horseshoe crab doesn't need new tools because the old ones still work. The ocean doesn't reward novelty for its own sake, it rewards what lasts. Some of these lasting forms are so ancient that they seem to have stepped straight out of the fossil record. The kilacanth, a fish once thought extinct for 65 million years, was rediscovered off the coast of South Africa in 1938, alive and unchanged. Its fins move like limbs, its scales are thick as armour, and its blood chemistry is built for deep, low-oxygen water. For scientists who saw it for the first time, it was like shaking hands with prehistory. The kilacanth had quietly continued its lineage through every cataclysm, hidden in dark caves and cold currents where time moves differently. That's what makes the ocean's memory different from ours. We measure history in human generations, maybe a few thousand years if we stretch it. The ocean measures it in epochs. It doesn't keep track of moments, it tracks eras. A single current may take centuries to complete one global circuit, carrying heat and nutrients from one side of the planet to the other before returning to where it started. While we build civilizations, wage wars, invent and forget technologies, that same current just keeps moving, its path unbroken. To the ocean, the rise and fall of humanity is barely a blink. But for all its stability, the sea is not frozen in time. It changes slowly, like a mind thinking in geological language. When the great ice sheets melted at the end of the last ice age, sea levels rose by more than 100 meters, drowning entire landscapes. Forests became reefs, river valleys turned into bays. Animals that once walked where fish now swim left bones that rest beneath coral gardens. Even now, the ocean continues to reshape the world beneath our feet, eroding, depositing, sculpting coastlines in silence. Among all this slow transformation, certain species endure as if they carry the ocean's own patience in their DNA. The nautilus, for example, spends its life spiralling upward and downward through water columns, guided by the delicate balance of gas and fluid inside its shell. It's been doing that for about 500 million years. When predators evolve new jaws, the nautilus simply sinks deeper. When temperatures change, it migrates. It doesn't fight evolution, it sidesteps it. That quiet adaptability is the secret language of survival. The same could be said for sharks. Long before mammals took to the sea, sharks were already there, shaped by pressures and opportunities we can barely imagine. Their skeletons are made of cartilage rather than bone, making them agile and efficient. Their senses are tuned to detect electrical impulses, the faint energy fields produced by living organisms. They can smell a single drop of blood in millions of gallons of water, but they can also sense the subtle heartbeat of a fish hidden under sand. These abilities didn't appear overnight. They are refinements accumulated through endless trial, mistake, and success, each generation passing down what worked best. When you look at a shark today, you're seeing an evolutionary idea so well tested that it barely needed editing for 400 million years. Even their reproductive strategies are ancient but effective. Some give birth to live young, others lay eggs encased in tough leathery cases known as mermaids' purses. The embryos inside grow slowly, nourished and protected, emerging as fully functional miniature versions of adults. There's a quiet efficiency to it, a kind of biological confidence that doesn't need reinvention. It's humbling to realize that creatures like these have survived all 5 of Earth's major extinction events. They witnessed the death of nearly everything else and kept going. When the Permian extinction wiped out 90% of marine life, sharks swam through the aftermath unshaken. When the asteroid struck at the end of the Cretaceous, their lineage endured. Not because they were invincible, but because they were adaptable. Evolution, after all, isn't about being the strongest or the smartest. It's about fitting in. The ocean's memory favours those who can adjust quietly. The horseshoe crab tells a similar story. With its helmet-like shell and blue blood, it looks alien to modern eyes, but its design is pure efficiency. It crawls across sandy flats using 10 legs, its tail spine not for defence, but for steering itself upright when flipped. Its blood contains copper instead of iron, giving it a metallic tint and remarkable antibacterial properties. Modern medicine depends on this blood to test for contamination in vaccines and surgical equipment. In a way, this ancient creature guards the health of the species that only recently began to understand time. When you think about the millions of years separating us from the first horseshoe crab, it's almost dizzying. Back then, the continents were arranged in strange shapes. The air was thicker with carbon dioxide, the sun was dimmer. Yet in all that time, these creatures barely changed. They have lived through environments that would kill us instantly. Toxic seas, low oxygen, extreme heat. The fact that they still thrive along modern beaches, often unnoticed, is proof of how deep the ocean's lessons go. But the ocean's memory isn't stored only in living creatures. It's written in sound. Whales sing through water that carries their voices for hundreds of kilometres. Some of those calls echo off seamounts and return minutes later, slightly altered by distance and temperature, like natural recordings of space and time. The sounds of the sea, the cracking of ice, the rumble of distant waves, the clicking of shrimp, all blend into what scientists call the soundscape. Within that soundscape, ancient species navigate as they always have, following vibrations more reliable than vision. Light fades quickly underwater, but sound travels far. That's why many of the oldest marine species rely more on vibration and pressure than on sight. The shark's lateral line, for example, is a sensory organ that detects minute changes in water movement. It's not a new invention. Even ancient fish had versions of it. The ocean remembers what works and it keeps refining it. If you could somehow compress all of ocean history into a single day, life would appear in the first few minutes after dawn. The first fish would swim by mid-morning, sharks by early afternoon, dinosaurs would stride onto land just before evening, mammals would emerge seconds before midnight. And humans, we'd arrive in the final flicker of that last second, barely a shimmer before the next day begins. Yet the creatures that first appeared in the ocean's early light are still here, carrying that ancient dawn inside them. That's what makes the sea feel eternal. When you stand on a beach and watch waves roll in, you're seeing the same process that carved continents, the same rhythm that once washed over trilobites and ammonites. The water touching your feet has circled the globe many times, evaporated, rained down, frozen, melted, and returned. Within it are atoms that once belonged to whales, to plankton, to ancient killers still ruling the ocean. You're standing in the middle of the planet's memory and it's touching you back. Of course, the memory isn't perfect. The ocean forgets too, but only in its own way. Coral reefs bleach when temperatures rise, erasing records of colour that took centuries to build. Plastic debris sinks into trenches where no fish should find it. Noise from ships drowns the songs of whales. Even the most ancient creatures are feeling the weight of modernity pressing into their rhythm. Yet somehow, they keep moving, just as they always have, their instincts older than our civilizations. When you think about that persistence, it changes how you see the ocean. It's not just water and waves, it's a mind that never sleeps, recording, reshaping, repeating. Every current is a neural pathway, every migration a thought. Life moves through it like signals in a vast brain made of salt and pressure. And in that slow, deliberate intelligence, the ancient killers still thrive. The jellyfish drifts, the shark glides, the nautilus spirals, the horseshoe crab crawls. Each movement repeats a gesture billions of years old. The ocean doesn't celebrate innovation the way we do. It celebrates endurance, the quiet art of existing without exhaustion. And maybe that's what we can learn from it. not how to dominate, but how to last. As we move deeper into these waters tonight, we'll meet more of these quiet rulers, the ones that shaped the ocean long before we knew it existed. Their designs tell stories of patience and precision, of survival not through strength, but through adaptation. They are the ocean's living memories, the ones that remind us that life doesn't always need to change to continue. It only needs to remember how. And somewhere below, beyond the reach of light, something begins to glow. It's older than fire, older than eyes, yet it burns softly in the black. The next part of our journey drifts toward that faint shimmer, a reminder that even in the oldest corners of the sea, the ancient killers have learned to shine. Down in the dim water where sunlight fades to suggestion, the shapes of the past move quietly. They don't advertise themselves, don't shimmer or call attention, yet there they are. Ghosts beneath the surface, alive in the present but built from the blueprints of worlds that ended long ago. These are the ocean survivors, the ones evolution refused to erase. They glide through time as easily as through water, carrying memories not in mind but in muscle, skeleton, and instinct. Every movement they make is a continuation of something ancient, something that outlived volcanoes, asteroids, and the slow rearrangement of continents. It's strange to think of evolution not as a ladder, but as a tide. Things rise, fall, and sometimes remain caught in quiet backwaters, unchanged because change isn't needed. That's what these creatures are. Not remnants, not leftovers, but designs that never failed. To watch one is to see what works so completely that even extinction lost interest. One of the most haunting examples of these old designs is the shark. Not the sleek Hollywood predator, but the real animal. Older, slower, endlessly diverse. Sharks appeared over 400 million years ago, long before trees, before flowers, before dinosaurs ever set foot on land. Their ancestors were smaller, boneless, more like ribbons of cartilage than monsters. Yet they mastered the art of predation early, perfecting a balance between speed, power, and efficiency that barely needed adjusting. Some early forms had armor plating and complex jaw structures, but over time, evolution stripped away the unnecessary, leaving only what was essential. The result was a creature so tuned to its environment that it could outlast empires of life. Even now, in every ocean, there are sharks whose lineage goes back almost unchanged to the early Paleozoic seas. The frilled shark, for example, looks less like a modern fish and more like a living fossil from the Devonian. Its long, eel-like body, its frilled gills, its rows of needle teeth. They speak of an ancient design built for deep, cold, silent hunting. When scientists first filmed one alive, it looked almost reluctant to belong to our era, as though it had accidentally wandered out of its own epoch. The Greenland shark is another ghost of evolution's patience. It can live for centuries, possibly up to 500 years, moving so slowly through the Arctic depths that barnacles grow on its skin. Its flesh is toxic to most predators, its metabolism glacial. It doesn't need speed. It survives by existing at the edge of motion. It hunts when it must, scavenges when it can, and drifts through dark water older than the nations above it. For a creature like that, time doesn't flow the way it does for us. It's just another current to move through. Every ghost of the sea has its own trick for defying time. The nautilus carries its home on its back, a coiled shell of perfect geometry. Each new chamber it builds is a record of its growth, a spiral archive of survival. The pattern hasn't changed in over 500 million years because it didn't need to. Its jet propulsion, its buoyancy control, its slow, deliberate life in the deep, all of it still works as it did when trilobites scuttled along the sea floor. When you hold a nautilus shell, you're holding a shape that predates every mammal, bird, and reptile that has ever lived. It's a design so elegant that mathematics, art, and architecture later borrowed its form without knowing its origin. There are others, Less known but equally persistent, the hagfish, for example, looks more like a piece of discarded rope than an animal, yet it's one of the oldest vertebrates still alive. It has no jaw, no true spine, and it defends itself by releasing clouds of thick slime that can choke a predator's gills. It's an absurdly simple defense, but effective enough that hagfish have survived since before vertebrates had bones. When threatened, it ties itself in knots to scrape off the slime and swim away. Primitive? Maybe. Successful? Absolutely. Then there's the lamprey, with its circular mouth lined with rasping teeth. It hasn't changed much since fish first evolved. It clings to other creatures, drawing blood, surviving off their strength. In some rivers, it's considered a pest. In others, a relic. To evolutionary biologists, it's a living reminder of how the first jaws may have formed. Watching a lamprey feed is like looking at a prototype, a step in the long design process that led to every predator since. Even creatures we consider beautiful, like sea turtles, are part of this lineage of persistence. They've been gliding through warm shallows and open oceans for more than 100 million years. Their ancestors swam alongside the last dinosaurs and didn't blink when the asteroid came. Today they still follow ancient routes, migrating thousands of miles guided by magnetic fields that haven't shifted in their memory. They return to the same beaches where their ancestors nested before humans had language. The sand changes, the temperature changes, the coastline erodes, but their instinct holds. Every hatchling that makes the impossible crawl to the sea is repeating an act that has been successful since the Cretaceous. It's easy to forget that what we call ancient isn't defined by age alone, but by endurance. Evolution's survivors aren't trapped in the past. They're evidence that life doesn't need constant reinvention. It only needs a method that works under pressure. In the deep sea, that pressure is literal. Tons of water bearing down on every square inch, crushing anything unprepared. Yet down there live the same forms that thrived before mammals existed. Deep-sea crustaceans, giant isopods, and ghostly white crabs feed on the remains of the modern world as if nothing has changed. Some of these creatures seem designed not for life, but for persistence. The kilacanth, with its slow metabolism, can go months without eating. The nautilus can live a century without ever needing to change its routine. The Greenland shark drifts so slowly that it barely burns energy. Each has found a way to live longer by living differently. The ocean rewards patience. What makes these creatures feel ghostly isn't just their age or appearance, but their indifference to our timeline. They move according to rhythms that ignore us completely. The shark doesn't care about climate models. The nautilus doesn't notice political borders. They exist in a continuum that began before us and will likely outlast us. When we study them, we're peeking into a kind of immortality, not the personal kind we fantasize about, but the evolutionary kind that plays the long game. And yet, these survivors are not invincible. The same slow pace that kept them safe for eons now makes them vulnerable. They reproduce infrequently, grow slowly, and depend on stable conditions. When the ocean warms too quickly or acidifies, they can't adapt fast enough. For creatures that measure time in centuries, change that happens in decades is a shockwave. That's why so many ancient species are now under threat, not from natural catastrophe, but from our acceleration. Evolution never practiced for us. Still, the persistence of these species offers something more than nostalgia. It's a window into what survival really means. We often imagine progress as improvement, smarter, faster, more complex. But evolution doesn't care about progress. It cares about continuation. The shark doesn't dominate the sea because it's perfect. It dominates because it fits. The jellyfish isn't eternal because it's advanced. It's eternal because it's efficient. These creatures remind us that life's ultimate goal isn't perfection, it's endurance. When you look closely at a jellyfish drifting near the surface, it's hard to believe it's older than the dinosaurs, yet its body is a masterpiece of minimalism. No heart, no brain, no bones. just a network of nerves that reacts instantly to its surroundings. It pulses forward using nothing but water, recycling energy with flawless precision. When conditions worsen, it can reproduce asexually, splitting and reforming. Some species can even revert to a younger stage of life, starting over instead of dying. In that way, they're not just survivors of evolution but rebels against it. They've found a loophole in the rules. There's a strange comfort in knowing that life can find so many ways to persist. Even after 5 mass extinctions, when almost everything died, the ocean always rebuilt itself using these same survivors as templates. The simple became complex again. The ancient gave rise to the new. The ghosts of one age became the ancestors of the next. Evolution's survivors are not static. They're the seeds of renewal. Think of coral reefs, ancient structures built by tiny creatures that have been around for hundreds of millions of years. Each coral polyp is delicate, short-lived, yet together they form massive cities that can last for millennia. They're living records of both stability and change. In their limestone skeletons, scientists can read centuries of ocean temperature, chemistry, and even storm patterns. They're archives of survival built molecule by molecule. Even microorganisms, the smallest and oldest of all, play their part as quiet rulers of time. Cyanobacteria, for instance, are the architects of Earth's oxygen atmosphere. Long before plants existed, they were performing photosynthesis, releasing oxygen that transformed the planet and made complex life possible. They're still doing it today, unchanged in form, still shaping the chemistry of the ocean. These are the true ancient killers, invisible but absolute. Without them, nothing else would breathe. The phrase, ghosts beneath the surface, could sound eerie, but it isn't meant to be. It's more a reminder that everything living now carries the past inside it. Every heartbeat, every breath, every instinct is inherited from something that survived long enough to pass it on. When a shark circles or a jellyfish pulses, it's not performing something new. It's repeating a gesture that worked billions of times before. There's something grounding in that realization. We tend to see ourselves as the latest step in evolution, the pinnacle of progress. But standing beside these old survivors, we look more like the newcomers we truly are. They've endured every cataclysm we fear, climate change, mass extinction, food scarcity, and done so without machines, governments, or plans. They simply adapted, slowly, silently, successfully. That's why scientists study them, not just for curiosity but for wisdom. The immune systems of sharks might hold secrets to resisting disease. The regenerative cells of jellyfish could one day teach us how to repair tissue. The structure of nautilus shells inspires designs in engineering. Even the humble horseshoe crab teaches us how to recognize danger in our own bloodstream. The ghosts of evolution are not dead relics, they're mentors. If you could descend far enough, past the point where light becomes memory, you'd find that the ocean floor is still alive with these quiet instructors. Giant amphipods crawl across the sediment, scavenging the remains of whales. Sea cucumbers filter silt as their ancestors did before vertebrates had jaws. Deep-sea worms glow faintly, signalling to mates in darkness that has existed unchanged for eons. Everything here moves slowly because slowness works. It's not laziness, but longevity. Even when we disturb their world with noise and nets, pollution and heat, they adapt as best they can. Some migrate deeper, some reproduce earlier. Some vanish into unexplored trenches waiting for the chaos above to pass. If time has taught them anything, it's patience. They've seen worse and survived. Perhaps that's why we find them so fascinating. They make time feel smaller. When you realize that the shark beneath your boat has been swimming the same way since before your species existed, it shrinks your sense of importance, but enlarges your sense of connection. The ocean isn't ancient because it's old. It's ancient because it's continuous. And as we move further into that continuity, deeper into the world these survivors guard, the light fades entirely. The surface becomes a rumour. Pressure tightens like a fist around every living thing. Yet something moves there, glowing softly, an inheritance from an age before the sun's light reached the earth. A reminder that not all killers need teeth or speed. Some rule by patience, by chemistry, by light itself. We'll drift closer now, following that faint shimmer into the realm of creatures that predate bones, that hunt not with jaws but with glow, the ocean's living lanterns, whose lineage began when the world was still young and dark. The shimmer fades as we rise slightly towards shallower waters, where the ocean floor begins to reveal texture again. Sand ripples like fabric, shells half buried in the silt, and small tracks mark where something ancient has passed not long ago. There, moving with an unhurried determination, is a shape that doesn't quite belong to any modern category. Its body looks like a shield forged by time, its legs tucked beneath like clockwork still running after hundreds of millions of years. The horseshoe crab has been making this same slow journey along the ocean floor since before the continents found their current shapes. When the world was young, it was already old. It isn't a crab at all, though its name suggests one. It's closer to spiders and scorpions, part of a lineage so ancient that it predates both. Its ancestors crawled through the shallow seas of the Paleozoic era, when life was just learning how to build skeletons. Those seas are gone now, replaced by others, yet the horseshoe crab has hardly changed. Its smooth, domed shell, its hinged tail spine, and its armoured legs have survived ice ages, asteroid impacts, and shifts in sea chemistry that erased most of its contemporaries. The ocean has sculpted it through pressure and patience into something that doesn't need improvement. The first thing you notice about it is the colour of its shell, a metallic olive that catches light like old bronze. It looks more like a piece of armour than a living creature. Beneath that armour are 10 legs, each tipped with small claws used for crawling, digging and feeding. Its compound eyes, though primitive, detect polarised light, allowing it to navigate even murky waters. 2 smaller eyes on top of its shell help it sense day and night, guiding it toward the shore when the moon is full. That migration, a slow mass movement toward beaches to lay eggs, is one of the oldest rituals on Earth. When they come ashore, the scene looks almost prehistoric. Hundreds of armoured shapes moving together in the moonlight, a tide of time returning to land. The horseshoe crab's body is a timeline. The outer shell, called the carapace, shows faint ridges marking growth. The tail spine, or telson, acts as both rudder and lever. When a wave flips the animal onto its back, it doesn't panic. It simply pushes the telson into the sand and rights itself with a motion it has performed for 500 million years. Every part of it serves a purpose that hasn't needed to change, but its most extraordinary feature lies within, in its blood. If you could see it outside the body, you'd be startled by the colour. Instead of red, it's blue, a pale sky-coloured liquid that looks almost delicate. That colour comes from copper, not iron. In our blood, iron binds oxygen, turning it red when oxidised. In theirs, copper does the same, forming hemocyanin. It's less efficient in warm conditions, but perfect for the low oxygen environments where these creatures live. Evolution didn't choose it by accident. It selected what worked for shallow, brackish waters long before air was breathable. The real secret of that blue blood, though, isn't just its colour, it's its sensitivity. Within it are special cells called amebocytes that detect bacterial toxins instantly. When exposed to even trace amounts of contamination, the blood clots, forming a gel that isolates the danger. For the horseshoe crab, this reaction is a simple immune defense, but for us, it became one of the most valuable discoveries in modern biology. In the 1950s, scientists learned to extract this substance, now known as limulus amebocyte lysate, or LAL. It became the global standard for testing medical equipment, vaccines, and intravenous drugs for bacterial contamination. Every syringe, every implant, every vial that enters a hospital is tested using this compound, or its synthetic alternatives inspired by it. Without it, modern medicine would risk invisible infection at every turn. The irony is almost poetic, that the safety of advanced human technology depends on a creature that hasn't changed in hundreds of millions of years. Each year during the breeding season, these ancient beings are collected by the thousands along the Atlantic coast of North America. Scientists and technicians carefully extract a portion of their blood, about a third of their total volume, and then release them back into the sea. The process isn't perfect. Some don't survive, but the industry has begun shifting towards synthetic substitutes, reducing dependence on the living animals. Still, for decades, our health rested quite literally on their endurance. The blue blood of the horseshoe crab connected our sterile hospitals to the primordial ocean. There's something humbling in that connection. When you hold a vial of vaccine, somewhere in its testing lineage is a trace of that ancient blue. It's as if a whisper from the Cambrian still lingers in the background of every injection, reminding us that the oldest survivors of Earth's oceans still keep us alive. They are not relics. They are our silent collaborators. The horseshoe crab's life cycle follows rhythms older than civilization. Each spring, when the tides rise under a full moon, they crawl ashore by the thousands to mate and lay eggs. The females dig shallow pits in the sand, depositing clusters of greenish eggs that will hatch into trilobite-like larvae. For the brief moment they're exposed to air, they bridge two worlds, the ancient sea and the modern shore. Shorebirds time their migrations to this event, feasting on the nutrient-rich eggs. Entire ecosystems depend on this yearly ritual, a ceremony so old that it probably began before the continents were arranged as they are now. The young that survive return to the sea, growing slowly, shedding their shells as they age. They mature over nearly a decade, molting through 16 or more stages. Each molt leaves behind a perfect, ghostly replica, an empty armour that looks alive until you touch it. Those discarded shells pile up along coasts, natural fossils waiting to be made. To walk among them is to walk through the ocean's ongoing memory, to see proof that time in water moves differently. What's remarkable is how quietly these creatures exist alongside us. You could stand on a modern beach and see them in the moonlight, just as someone might have done 10,000 years ago, 100,000 years ago, or 1,000,000. The waves sound the same, the sand feels the same, and the animals themselves are unchanged. We measure progress in decades, they measure it in epochs. When scientists study the horseshoe crab's vision, they find something almost paradoxical. Its eyes are simple, yet they were the foundation for our understanding of how complex vision evolved. Decades of research into the horseshoe crab's optic system led to discoveries about photoreceptor cells that apply directly to human eyes. A creature that seems so primitive taught us how our own sight works. It's another quiet link in the long chain between the ancient and the modern. Their shells tell a similar story. Made of chitin and protein, they resist decay and provide protection against both predators and infection. Engineers study their structure to design lightweight, resilient materials. The segmented armour distributes force evenly, absorbing impacts without breaking, a principle useful in everything from robotics to protective gear. What evolution refined through survival, we repurpose through design. Even their behaviour holds lessons. Horseshoe crabs don't compete fiercely for territory. They coexist, overlapping without much conflict. Their survival doesn't depend on domination but on timing, cooperation and endurance. In the hierarchy of predators, they aren't killers. They feed on worms, clams and algae, sifting through sand for what the tides leave behind. Yet despite their peaceful nature, they've outlasted nearly every apex predator that ever lived. Perhaps longevity favours those who take less. There's something almost comforting about their slowness. Watching one move feels like watching an old clock tick, steady, patient, purposeful. They don't rush to feed or flee. They don't need to. Their armour protects them from most threats, and their ancient physiology ensures they can survive in poor oxygen conditions that would suffocate newer species. When storms churn the water, they dig in and wait. When the tide recedes, they follow it with practiced ease. They don't fight the ocean, they move with it. For a creature that seems so unchanged, the horseshoe crab has witnessed unimaginable transformations. It survived when trilobites disappeared. It watched the first fish evolve, the first amphibians crawl onto land, the first dinosaurs roar and fall silent. It saw the continents drift apart and meet again. It endured global freezes and heat waves, mass extinctions and resurrections. Its body has been a constant in a world that never stops shifting. And now, in the age of humans, its greatest challenge may come not from nature but from us. Habitat loss, pollution, and overharvesting for bait and biomedical use threaten populations that have remained stable for millions of years. On some beaches, their numbers are dwindling. Conservation efforts are increasing, but recovery takes time, and time is something we spend quickly. For a species that measures its life in centuries, our urgency can be dangerous. Yet even with these pressures the horseshoe crab endures, it has done so through every crisis so far. Its eggs still hatch in the sand. Its blue blood still clots at the first hint of danger. Its silent migration still marks the turning of the tides. It reminds us that survival doesn't always require complexity or intelligence, just resilience and the ability to keep doing what works. Sometimes people see them washed up on beaches and mistake them for dead. Their shells empty, their bodies motionless, but often they're just resting, waiting for the next tide. If you help one back into the water, it will resume its journey as if nothing happened. That small act reconnects two species separated by 500 million years of evolution. One fragile and recent, one ancient and enduring. In a way, we owe them more than gratitude. Our science, our safety, even our understanding of life's persistence are all linked to this quiet creature. It carries its history not as weight, but as proof. It doesn't need to adapt constantly because it already adapted perfectly once. The next time you see the sea shimmer under a full moon, imagine what's happening beneath that light. Thousands of armoured shapes gathering at the edge of the water, guided by instincts older than language. They've been doing it since before mammals existed, and they'll likely keep doing it long after we're gone. The rhythm won't stop. The moon will rise, the tide will follow, and the horseshoe crabs will climb ashore as they always have, carrying with them the blue secret that connects the oldest oceans to our most modern lives. And as the tide pulls them back again, the light fades, the surface quiets, and something softer begins to drift above, transparent, delicate, pulsing. The oldest jellyfish, the eternal drifters, move through the water like memories made flesh, continuing the story of what it means to last when everything else changes. Above the quiet migration of the horseshoe crab, something lighter moves. The waves roll in slow, steady breaths, and within them bodies of light drift without effort. You could mistake them for fragments of the sea itself, translucent, weightless, trailing ribbons that catch the moon and fold it into themselves. They are jellyfish, the simplest and perhaps most enduring creatures the ocean has ever made. They've floated through the water for more than 500 million years, long before fish had bones or eyes. Every one of them is a reminder that life doesn't need complexity to survive. Sometimes it only needs rhythm. To see a jellyfish up close is to see time made visible. There's almost nothing to it. A bell of gelatin, tentacles hanging below, a soft pulse repeating over and over. No bones, no heart, no brain. Yet it's alive in a way that challenges what we think life requires. Its body is more than 90% water, held together by a thin film of protein and nerve cells. Those nerves don't think as we do. They respond. When touched, they contract. When light dims, they slow. Its existence distilled to the simplest motion. Expand, contract, drift. That simplicity has allowed jellyfish to persist while most other creatures disappeared. They have no lungs to fill, no skeletons to fossilize. no complicated organs to fail. They rely on the ocean to move them, using its currents as both transport and shelter. When food is plentiful, they multiply quickly, budding new forms from their polyps along rocks and reefs. When conditions worsen, they shrink, slow down, or revert to earlier life stages. Every stage is a contingency plan. Every design choice is survival through reduction. If you were to watch one long enough, you'd notice that its movement isn't random. The gentle pulsing of its bell creates a flow that draws water in and pushes it out in perfectly efficient cycles. It wastes almost no energy. Engineers studying jellyfish propulsion have found that their motion ranks among the most energy efficient in the animal kingdom. They move more by allowing than by forcing, using the fluid's natural resistance to propel themselves. The ocean carries them not as passengers but as partners. The oldest jellyfish fossils, pressed into stone from the Ediacaran period, show almost the same structure as the living ones drifting today. Those faint imprints are more than 500 million years old, yet the outline is identical. The bell, the tentacles, the symmetry of 4 internal canals. No redesign necessary. They were right from the beginning. To call them timeless isn't exaggeration. They've survived all 5 mass extinctions that nearly erased life from the planet. When the seas turned acidic, they persisted. When oxygen levels plummeted, they adapted. When the dinosaurs fell, they pulsed onward as though nothing had changed. And in today's oceans, as temperatures and nutrients shift again, they continue to thrive. In some places, their numbers are even increasing, forming blooms so vast they fill entire bays with a slow, silent congregation. Some scientists see this as a sign of imbalance, others as proof that the ocean, once again, leans on its oldest survivors to stabilize itself. What's easy to miss about jellyfish is that their lives are cyclical in ways almost alien to us. Most begin as tiny polyps attached to rocks or shells. Those polyps can stay dormant for years, waiting for the right conditions before budding new medusae, the free-floating forms we recognize. It's a life that can pause and resume, stop and restart. Some species, like Turritopsis dohrnii, take that idea even further. When injured, starved or stressed, they can reverse their life cycle entirely, transforming back into a polyp and starting over. It's not metaphorical regeneration, it's biological. They age backward. The process has no known limit, making them effectively immortal under the right conditions. In labs, scientists have watched this happen repeatedly, a continuous loop of birth without death. That kind of resilience raises questions not only about survival, but about what it means to end. In the ocean, endings are rare. Everything becomes something else. The jellyfish, by mastering the art of reversal, simply made that process internal. Instead of waiting to die and decay, it dissolves itself and begins anew. The mechanism is still not fully understood, but it suggests that aging, the slow accumulation of damage we accept as inevitable, is not universal. In jellyfish biology, time can be folded, ignored, or undone. If you were to hold a jellyfish, you'd barely feel it. Its body is mostly water, its edges dissolving into your touch. Yet that fragility hides one of nature's most potent defences. The tentacles that trail beneath its bell contain thousands of specialised cells called nematocysts, tiny capsules under pressure, each armed with a coiled, venomous thread. When triggered, they fire faster than a bullet, penetrating and injecting toxins into prey or predator. For small fish or plankton, the result is instant paralysis. For humans, depending on the species, it can range from a mild sting to something deadly. The box jellyfish of the Indo-Pacific, for example, carries venom capable of stopping a heart in minutes. It's a perfect contradiction. A creature that appears weightless and harmless, yet holds one of the most powerful weapons in the sea. Despite their sting, jellyfish aren't hunters in the way we imagine. They don't chase or stalk. They float, letting currents deliver their meals, small fish, plankton, larvae, directly into their drifting nets. Their digestive systems are simple. Food enters, is broken down, absorbed and expelled from the same opening. It's a cycle, efficient and complete, with no waste of motion. They are living feedback loops. When the ocean changes, jellyfish adjust without protest. Warmer temperatures, lower oxygen and fewer predators often favour them. They bloom where others decline. In this way, they become indicators of imbalance, a kind of warning written in flesh. Coastal communities sometimes see massive swarms clogging fishing nets, stinging swimmers, or shutting down power plant intakes. Yet even in those disruptions, they're not villains. They're signals, reminders that the ocean remembers imbalance too. When overfishing removes their competitors, when pollution alters the water's chemistry, jellyfish fill the gaps. They thrive where complexity falters. Their presence throughout the world's waters makes them nearly universal. From polar seas to tropical lagoons, from surface drifters to deep bioluminescent hunters, jellyfish occupy every niche. Some glow with their own light, turning the black water into slow-moving constellations. Others are invisible until the light hits them just right, refracting like glass. In the deep sea, where sunlight never reaches, bioluminescence becomes their language. Pulses of blue or green communicate movement, confusion, or warning. A flash may attract prey or deter predators. Each species has its own rhythm, its own flicker. Down there, light is as old a survival strategy as any weapon. If you were to travel through that darkness, you'd see whole galaxies of jellyfish drifting together, lighting up and fading again. Their glow comes from chemical reactions within their cells, often involving a protein called luciferin and an enzyme called luciferase. When oxygen mixes with these compounds, light is produced, not heat, just pure luminescence. It's the same chemistry that fireflies use on land, but in the ocean, it's been around far longer. In some species, that glow serves as camouflage, blending their silhouettes with faint downwelling light. In others, it's a lure, a mimicry of prey. In all cases, it's a survival tactic honed across deep time. When scientists study jellyfish, they don't just learn about marine biology. They learn about biochemistry, neurology, and even physics. One of the most revolutionary tools in modern medicine, the green fluorescent protein used to illuminate cells under microscopes, came from a jellyfish species, Aquaria victoria. This discovery allowed researchers to map the inner workings of living cells, track diseases, and understand genetics with unprecedented clarity. The same light that guides jellyfish through darkness now helps us navigate the hidden spaces of our own biology. It's another reminder that even the simplest creatures can leave the deepest marks on science. What's remarkable is that despite all our knowledge, jellyfish remain enigmatic. They have no central brain, yet they exhibit coordinated behaviours. They can sense orientation, gravity and light without eyes in the conventional sense. Their nerve nets act like distributed computers, processing signals locally rather than centrally. This decentralized intelligence is elegant. It avoids single points of failure. If one part is damaged, the rest continues functioning. Engineers study this as a model for resilience in robotics and network systems. Once again, the ocean's most ancient drifters quietly teach lessons about endurance and adaptation. Some species form symbiotic relationships that further blur the line between simplicity and sophistication. Juvenile fish often hide among jellyfish tentacles, safe from predators that can't risk a sting. In some cases, the fish feed on the jellyfish's leftovers, while the jellyfish benefit from the fish scaring away parasites. It's an arrangement so subtle that neither species truly dominates. Even here, the jellyfish's way of life revolves around balance, not conquest. Their reproduction too follows cycles that defy our sense of time. A single jellyfish can release thousands of eggs or sperm into the water, a broadcast method depending entirely on chance and abundance. Most will never meet, never form new life. But enough do, sustaining lineages that have never been interrupted. There is no competition for mating rights, no displays, no parental care. Just release, drift, and renewal. life continuing through sheer probability. Watching jellyfish can feel hypnotic. Their movement slows thought itself. Aquariums use them to calm visitors, their pulsation setting a natural tempo that mirrors slow breathing. It's not just aesthetic. Something about their rhythm resonates with the human nervous system, triggering patterns of relaxation. Perhaps it's because we recognize something familiar in them, a simplicity our complex lives have long lost. Beneath our reasoning and urgency, we too rely on cycles: heartbeat, breath, sleep, waking. The jellyfish is that idea reduced to its purest form. If there's one thing they reveal, it's that survival doesn't always come from struggle. Sometimes it comes from surrender, to current, to rhythm, to change. While land animals evolved muscles, lungs and intelligence to fight their environment, jellyfish evolved transparency and compliance. They let the ocean move them. In return, the ocean never left them behind. In mythology, the sea often stands for memory, transformation, eternity. The jellyfish embodies all of that without metaphor. It doesn't just survive through time, it makes time irrelevant. When it drifts, it isn't going anywhere specific. It's simply being carried, existing where it is, when it is. That quiet endurance may be why they've outlasted nearly every other design nature has tried. They remind us that permanence sometimes hides in motion, not in stability. Yet even they are not immune to us. Pollution clouds the waters they thrive in. Plastic bags mistaken for food choke sea turtles that would otherwise keep their numbers in check. Chemical changes in the ocean affect how they reproduce. Still, they continue to adapt. Some species are thriving in urban harbours, around docks, in power plant effluents, turning our disturbances into opportunity. Where others fail, they find new space. There's a lesson in that, though it isn't comfortable. When ecosystems collapse, the jellyfish bloom. Their success is our warning. The ocean remembers imbalance and compensates in its own way. If the balance tips too far, the future may belong again to creatures like these. Simple, self-sufficient, untroubled by complexity. Life always continues, but not always as we expect. For now, they drift. Beneath the surface in the quiet blue, countless jellyfish pulse in time with the sea's heartbeat. Their bodies catch the moonlight, scatter it, and disappear again. They are the ghosts of the first oceans, the architects of light, the oldest proof that simplicity is enough. As we move deeper into this endless archive of the sea, another shadow forms, sleek, deliberate, built not for drifting, but for control. A shape that embodies precision rather than surrender. Fins cut through the dark, and the ocean, for a moment, seems to hold its breath. The ancient killers with teeth of evolution glide forward. The sharks are waiting. From the still drift of the jellyfish, the light fades again and gives way to something with more intent. A shape appears, not fragile, not slow, but carved by movement itself. It cuts through the water without resistance, guided by lines so efficient they might as well have been drawn by evolution's steady hand. The shark has arrived, and the ocean rearranges itself around it. Even before we can see it clearly, we feel its presence, not as danger, but as precision. Every beat of its tail, every flex of muscle is economy. It wastes nothing. It hesitates at nothing. In a world shaped by survival, it is the ocean's oldest perfection of balance. The first sharks swam here nearly 450 million years ago. Back then, life was still experimenting, testing shapes and systems that might endure. Some creatures armoured themselves in heavy plates, others hid, burrowed, or filtered the sea for food. The early sharks chose motion. Their bodies, made not of bone but of cartilage, gave them flexibility and lightness. They were the first true masters of movement. Their teeth evolved as replaceable tools, rows upon rows continuously renewed. Their skin, covered in tiny scales shaped like teeth themselves, reduced drag and noise. They became living streamlines long before physics had a name. If you were to strip away everything unnecessary from the idea of a predator, what would remain would look very much like a shark. Yet it's wrong to think of them as simple killers. What they do is not aggression but equilibrium. They regulate, they edit. By removing the sick, the weak and the dying, they keep marine ecosystems healthy. Without them, prey species multiply beyond capacity, reefs collapse, and balance dissolves. The shark's reputation as a threat to humans overshadows its real role as guardian. It rules not by terror, but by maintaining the natural order. The diversity of sharks reveals how deeply they've tuned themselves to every oceanic environment. The whale shark, gentle and immense, filters plankton through its open mouth, moving with the calm assurance of something too large to rush. The hammerhead's strange head, wide and flat, gives it stereo vision and heightened sensory precision, detecting even the faint electrical signals of hidden fish. The mako moves like liquid metal, the fastest of them all, slicing through open water at speeds that seem impossible for flesh. The Greenland shark, slow and cold, measures its life in centuries. Each one is a different interpretation of the same elegant equation. Adapt perfectly to a niche, and time will leave you alone. Their senses extend beyond our understanding of perception. A shark's ability to detect electric fields, through organs called ampullae of Lorenzini, is one of the most refined in nature. It allows them to sense the faint heartbeats of buried prey, or the orientation of the planet's magnetic field for navigation. They read the ocean the way we read words, decoding invisible information written in current and charge. No GPS, no light, no noise, just instinct honed by 500 million years of necessity. For all that time, their design has barely changed. Fossilized shark teeth from the Devonian period could be mistaken for modern ones. The classic form, tapered body, dorsal fin, crescent tail, emerged early and never needed replacing. They've lived through every mass extinction, losing species but never the idea of what a shark is. Evolution doesn't fix what isn't broken. When people fear sharks, it's usually a fear of misunderstanding. The movie monster version, all teeth and mindless hunger, bears little resemblance to reality. Most sharks avoid humans entirely. The few encounters that turn violent are accidents of curiosity or confusion, not intent. To a shark, we're awkward, noisy visitors in a world that was never ours. It doesn't hate or hunt us, it simply investigates. The fear we feel looking into its eyes is really the fear of seeing something that doesn't need us at all. In those eyes, dark, expressionless, unblinking, there's a kind of stillness that's unsettling. But it's not emptiness, it's focus. Sharks don't show emotion as we understand it, yet their awareness is undeniable. They process information with calm efficiency. Every flick of a fin, every subtle shift of their path has purpose. To watch one is to witness movement stripped of excess. When scientists study their anatomy, they find evidence of evolutionary economy everywhere. Their liver is massive, rich with oils that provide buoyancy. Their skeleton's cartilage flexibility absorbs shock during rapid turns. Their scales, or dermal denticles, are micro-engineered armour, each one a ridged tooth that channels water flow. Modern swimsuits, ship coatings, and even turbine designs borrow from this texture. The ocean's engineers got there first, hundreds of millions of years ago. And yet, for all their efficiency, sharks live vulnerable lives. Many species reproduce slowly, giving birth to few young after long gestation. Some take decades to mature. This strategy worked perfectly for eons when the ocean was vast and unhurried. But it makes them fragile in the modern era, where industrial fishing, habitat loss, and fin harvesting remove them faster than they can replace themselves. A creature that has survived asteroids and ice ages is now endangered by nets and ignorance. It's a cruel irony, the ultimate survivor undone not by nature, but by haste. There's something tragic in watching a species that once ruled the sea reduced by fear and profit. Sharks are not symbols of danger. They're symbols of endurance. Their disappearance would unravel ecosystems that depend on their presence. Coral reefs, for instance, thrive in part because sharks keep herbivore populations balanced, preventing algae from overrunning corals. Remove the sharks, and even the smallest polyps feel the effect. Everything in the ocean is connected by invisible threads of dependency, and sharks are some of the strongest fibres in that weave. Still, some species endure despite the odds. The great white, the tiger, the bull, apex hunters that adapt to new conditions with quiet persistence. Their movements span thousands of miles. Satellite tracking reveals migrations that cross entire oceans, following temperature gradients, currents, and prey distributions with precision scientists are only beginning to understand. To them, the ocean isn't divided by borders or names. It's one continuous field of possibility. If you could travel with one, you'd see how their world unfolds. Light dimming to green, then blue, then black. Pressure increasing, temperature dropping. Still, the shark glides as if the environment were built for it. Its gills flare gently, its body flexes, and it vanishes into the dark without effort. In that moment, the ocean looks exactly as it did when life was young. To call them architects of fear says more about us than about them. Fear is a human invention, born from the imagination of prey that no longer remembers being prey. Sharks simply are. Their presence keeps the system honest. When we see them, we remember what it feels like to be part of something larger, not the top of it. They remind us that dominance isn't permanent and that balance is never optional. In the ecosystem, they are both the sword and the scale. When food is plentiful, they cull. When it's scarce, they move. Their movements trigger changes in the behaviour of prey species, which in turn affects the plants and microorganisms below them. It's a cascade of influence, subtle but absolute. Remove the top, and the structure below collapses. The term keystone species barely captures their importance. Without sharks, the ocean loses its architecture. Sharks also connect the visible and invisible worlds of the sea. By feeding on the dead or weak, they recycle nutrients. Their waste fertilises phytoplankton, which produce the oxygen we breathe. Every breath we take carries a trace of their ecological labour. We fear their bite but forget their gift. The air above us owes something to the teeth below. Even their deaths contribute. When a shark's body sinks, it feeds the deep sea for months, creating oases of life on the otherwise barren sea floor. Scavengers gather, bacteria bloom, energy moves through levels unseen. In that sense, they're not just predators but providers. Every part of their life cycle sustains others. To study them closely is to see intelligence expressed through instinct. Sharks navigate vast distances using cues so faint they defy our instruments. They can detect subtle changes in salinity, temperature, and electromagnetic fields. Some species return to the same nursery bays year after year, guided by memories we don't yet know how to measure. Their sense of place rivals any migratory species on land. There's a quiet order to their hierarchy too. Some species hunt alone, others in loose groups. They rarely fight without purpose. Displays of dominance are brief, decisive, and resolved without excess violence. They communicate through body language, posture, swimming patterns, proximity. It's an old language, older than sound, spoken through motion and respect. In recent years, divers and researchers have begun to challenge old narratives about shark aggression. Many describe encounters that feel less like confrontation and more like mutual curiosity. A diver remaining calm, holding position, often sees the shark approach, circle, and leave without incident. The animal reads the situation, assesses, and decides. It's not mindless hunger, it's discernment. They're observers as much as hunters. That observation goes both ways. We study sharks with sonar, cameras, and satellites. But the truth is we're latecomers to their world. They were mapping this planet's waters before continents had settled into place. Their roots trace the planet's ancient geography. Their DNA holds records of climate change older than human civilization. Every generation of shark is a continuation of data collected since life began. Even their teeth, scattered across seabeds, serve as a fossil record of evolution. Each one tells a story of diet, habitat, and adaptation. Smooth-edged teeth for soft prey, serrated ones for flesh, flattened ones for crushing shells. Paleontologists use them like calendar pages, tracking the rise and fall of ecosystems through the shape of a predator's smile. The ocean keeps no written archives, but in the sediment of time, it leaves these sharp signatures of continuity. Among all the ocean's old inhabitants, the shark represents balance perfected by necessity. It is evolution's reminder that the best solutions are sometimes the simplest: speed without waste, strength without excess, hunger without cruelty. When we think of ancient killers still ruling the ocean, we picture Jaws, but what truly rules is balance. The shark enforces it with quiet, relentless precision. Even now, as climate shifts and human activity strains the sea, some species adapt in ways that echo their ancestors' endurance. Great whites move into cooler waters. Reef sharks adjust their feeding grounds to follow altered currents. The genetic flexibility that kept them alive through 5 mass extinctions is still at work. Evolution didn't stop when we arrived. It continues beneath our notice. Watching one glide beneath a boat, silent and self-assured, you realise how temporary our dominion is. The shark doesn't need progress or approval. It doesn't care about our technology or fears. It swims the same path it did long before we named it. To it we are passing weather, a momentary disturbance on a surface it will outlive. That's perhaps why people feel awe as much as fear when they see one in the wild. It's not the threat of teeth, it's the confrontation with time. The shark is an unbroken lineage, a survivor that has seen the planet reinvent itself again and again. To meet its gaze is to meet continuity. And as it moves away, disappearing into the blue, the water closes without a trace. The balance remains, restored and silent. Above, sunlight filters down through the currents, touching creatures of every size, from the smallest plankton to the largest whale, all part of the same ancient system the shark maintains. But even the ocean's architects are not alone in endurance. Along its edges, in brackish waters and warm deltas, another ancient killer waits, one that crawled from the rivers into salt and back again, armoured in patience and built for ambush. Its lineage is as old as the shark's, its presence as commanding. The crocodile and its saltwater kin lie just beyond the surf, watching the tide with eyes that remember both land and sea. At the edges of the ocean, where salt and fresh water meet and blur into each other, the rules of survival shift. The tide moves in 2 directions, bringing the strength of the sea and the calm of the rivers together in a single, unstable place. It's here, in the mangroves and estuaries, that another ancient survivor waits. The water is still. The air feels thick. Nothing stirs, and yet everything watches. Beneath the surface, a pair of eyes breaks the tension. Yellow, steady, unreadable. The saltwater crocodile doesn't move. It doesn't need to. It has already won the moment by doing nothing at all. The saltwater crocodile, Crocodilus porosus, is the largest living reptile on Earth, a creature that seems carved from memory itself. It can grow beyond 6 meters in length and weigh over a ton, but its true power isn't its size. It's the patience built into its design. Every muscle, every scale, every silent breath through its nostrils is a lesson in restraint. The ocean around it moves quickly. It does not. It belongs to the water but isn't bound by it. It can live in rivers, swamps, lagoons, and the open sea. Few creatures have learned to cross boundaries as easily. When the tide brings salt into the river mouths of northern Australia, Southeast Asia, or the Indian subcontinent, the saltwater crocodile moves with it. Its name suggests confinement to salt, but that's misleading. These reptiles are masters of adaptation. They can tolerate full seawater, brackish mangroves or fresh rivers, regulating their internal salt balance through specialized glands in their tongues. They can travel for weeks across open ocean, using currents as invisible highways between islands. Sailors have reported seeing them far from shore, eyes and nostrils the only visible signs, drifting like logs. They are not lost when they leave land. They are expanding their territory. That mobility makes them more than river predators. They are coastal architects shaping the ecosystems where land and sea meet. When they patrol estuaries, they keep fish populations balanced, preventing overgrazing of aquatic plants. When they ambush water birds or mammals near the edge, they recycle nutrients from land back into the marine system. Their presence links the two worlds. Evolution built them with precision. Their lineage stretches back over 200 million years to the early Mesozoic era when dinosaurs first appeared. Back then, their ancestors, the crocodilomorphs, occupied a wide range of roles. Some ran on land, some swam in the sea, some even hunted like wolves. But the saltwater crocodile's direct lineage chose a different strategy: patience, ambush, endurance. Over time, their bodies flattened, their tails strengthened, and their jaws became instruments of absolute power. A saltwater crocodile's bite is the most powerful ever measured in a living animal, over 3,000 pounds per square inch. When it closes its jaws, bones break before the sound can reach the air. Yet that violence is only a fragment of its story. Most of its life is spent still, conserving energy with the efficiency of a machine. It can remain motionless for hours, even days, waiting for the right moment. The moment arrives when its prey, lulled by the quiet, steps too close. The strike that follows is not rage or hunger, but reflex, a movement older than language, perfected long before humans existed. Their hunting technique is an engineering marvel of precision. They use the element of surprise combined with sensory systems so refined they can detect the faintest ripple. Along the jawline, small black paws called integumentary sense organs pick up vibrations in the water, allowing the crocodile to locate movement even in complete darkness. Its nostrils and eyes sit high on the head, so it can breathe and watch while keeping the rest of its body submerged. When it lunges, the attack is a single fluid motion, jaw, tail and water colliding in a burst of controlled chaos. The prey rarely has time to react. Once captured, the crocodile doesn't chew. Its teeth are meant for gripping, not cutting. It performs a maneuver known as the death roll, twisting its body with immense force to tear flesh apart or disorient large animals. The act looks brutal, but it's not mindless. It's a learned, efficient technique passed down through millions of years of refinement. Every twist, every spin, every pull is physics and instinct intertwined. It's easy for us to see such precision and mistake it for cruelty, but cruelty requires intent, and the crocodile has none. It kills because that's what survival demands. It eats when it must and waits when it can. Its metabolism is so slow that it can go months without a meal. A single large catch can sustain it through an entire season. Energy conservation is its real weapon, the evolutionary solution that allowed it to outlast creatures that burn themselves out in speed or excess. When it's not hunting, it's territorial. Males guard stretches of river or coastline fiercely. Their bodies bear the scars of battles fought in the murky shallows, long gashes that heal slowly but never fade completely. Those scars are history written on skin, each one a record of dominance or defeat. They bellow low rumbles that vibrate through the water, announcing their presence to rivals and potential mates. Even the sound is ancient, more felt than heard, like the heartbeat of the place itself. Females, smaller but no less formidable, guard their nests with equal intensity. They build them out of mud and vegetation, hidden among mangroves, and lay eggs that incubate in the heat of decomposition. The temperature of the nest determines the sex of the hatchlings. Cooler sand produces females, warmer sand produces males. It's a delicate balance, one easily disrupted by environmental change. When the eggs hatch, the mother carries the fragile newborns in her mouth to the water, a tenderness that seems almost out of character for a creature known for ferocity. But that's the thing about ancient designs. They contain contradictions that work. The same jaws that can crush bone can also cradle life. Once the young reach the water, their odds are uncertain. Birds, fish, and even other crocodiles prey on them. Only a few survive to adulthood, but those that do enter a lineage that has barely altered its blueprint since the age of dinosaurs. The skeleton of a saltwater crocodile today could be placed beside one from 100 million years ago, and the differences would be minor. Evolution doesn't need to reinvent perfection. They are not the only survivors of their family. The Nile crocodile patrols Africa's great rivers. The American alligator dominates the southern swamps. The gharial with its long narrow snout hunts fish in India's rivers. Each represents a different adaptation of the same template, but only the saltwater crocodile conquered the sea itself. Its range extends farther than any of its cousins, from India to northern Australia, from the Solomon Islands to parts of Southeast Asia. It's not a regional creature, it's a global relic. Its ability to cross open ocean seems almost impossible for a reptile, yet it does so with deliberate strategy. It rides surface currents, maintaining buoyancy by regulating the air in its lungs. It can hold its breath for over an hour, letting the sea carry it as if it were driftwood. Satellite tracking has confirmed journeys of hundreds of kilometres across saltwater, long, patient migrations between islands. Carried by tides it doesn't resist. The crocodile doesn't conquer the ocean, it borrows its strength. For all its dominance, the saltwater crocodile is not invulnerable. It depends on coastlines and wetlands, environments increasingly at risk from development and climate change. Mangrove destruction, pollution, and human conflict threaten its strongholds. In some places, it's hunted as a danger to villages. In others, protected as a symbol of wild resilience. Its population fluctuates with our tolerance. And yet, like every ancient survivor, it adjusts. Some individuals adapt to living near human settlements, scavenging or hunting livestock. Others retreat deeper into protected waters. Their patience outlasts our policies. What makes the saltwater crocodile remarkable is not just its age, but its intelligence. Studies have shown that they learn patterns, the habits of prey, the routines of people, the timing of tides. They remember locations, anticipate opportunities. They've been observed stalking boats, waiting for predictable moments when fishermen discard waste. They can plan in their way, not through abstract reasoning, but through perfect familiarity with the environment. That awareness gives them an edge few animals possess. Their communication, though limited, is complex. Hatchlings chirp from within their eggs before hatching, prompting the mother to uncover the nest. Adults use low-frequency sounds and body postures to signal aggression or submission. Some of these signals are even visual: a raised snout, a splash, a sideways lunge. It's an old language, efficient and functional, carried unchanged across generations. Despite their fearsome reputation, attacks on humans are rare compared to our impact on them. Most occur when people enter their territory unaware or provoke them out of misunderstanding. To the crocodile, we're just another shape that breaks the surface tension. It doesn't hunt us, it reacts. The few who have observed them closely describe not malice but calculation. They seem to weigh risk and reward before every move. That deliberation is part of what keeps them alive. They spend much of their time basking, regulating body temperature under the sun, half in water, half on land. The position looks lazy, but it's anything but. It's thermoregulation, energy management, the kind of optimization that keeps a cold-blooded giant efficient in any climate. Every minute of stillness is purpose. When you look at one up close, what you see is a living mosaic of evolution's discipline. The ridged skin, the scales arranged like interlocking shields, the narrow pupils scanning even the smallest ripple. It's the product of refinement, not excess. The saltwater crocodile isn't the ocean's most elegant creature, but it may be one of its most complete. It has everything it needs and nothing it doesn't. It's fascinating to imagine the world through its perspective. Time, for it, doesn't move as we experience it. A century is not a lifetime's limit, but a possibility. A single crocodile might live to see its grandchildren's grandchildren hatch. It doesn't rush toward goals because its existence is continuous. Hunger, territory, reproduction. These are not ambitions, just cycles repeating as they always have. The saltwater crocodile is what happens when a species learns to live entirely within its environment instead of against it. Even the way it swims reflects that harmony. Unlike the shark, whose constant motion keeps it from sinking, the crocodile glides near the surface, propelled by slow, sweeping motions of its tail. It can float motionless for hours, nostrils just above water, body perfectly level. It's a predator that has mastered invisibility without ever leaving the open. Its success depends on being seen too late. At night, its eyes reflect the moonlight in dull red flashes. Locals along northern coasts sometimes spot those lights flickering across the river like embers. To them, the crocodile is not just an animal, but a reminder that the wild still watches. It's both feared and revered, a guardian of boundaries between human and natural worlds. In many cultures, it symbolizes power, patience, and death, not as punishment, but as balance. The ocean may belong to the shark, but the shore belongs to the crocodile. The idea that one creature could outlast empires isn't fantasy, it's fact. The saltwater crocodile has survived the extinction of dinosaurs, the rise and fall of ice ages, and the reshaping of continents. It has watched civilizations appear and vanish along its coasts. It doesn't change because it doesn't need to. Change happens around it. And yet, as steady as it seems, it's not frozen in time. Its populations shift, its ranges expand or contract, its habits evolve subtly. Even ancient perfection continues to adjust. That's the secret of endurance, not resistance to change, but selective acceptance. The saltwater crocodile doesn't fear change, it filters it. When the tide rises again, the crocodile returns to the water. It slides in without a sound, leaving no trace on the surface. The ripples vanish. The river, the ocean, the estuary, they become one seamless world again. For a moment, nothing moves, but everything continues. Beneath the water, another current of life flows, quieter, smaller, older still. A spiral shape turns slowly in the dim light, its shell divided into perfect chambers, each one marking time in silence. The nautilus drifts there, carrying its own fossilized past forward, the next ancient survivor in the ocean's unending line. Beneath the slow shadow of the crocodile, deeper where the waves lose their colour and sound moves faster than light, the water grows colder and heavier. The darkness here isn't empty. It's thick, like a fabric woven from centuries of stillness. Within that stillness moves a small, deliberate shape, spiralling through space with quiet precision. Its shell catches what little light remains, revealing faint bands of ivory and rust, like the rings of a planet. The nautilus drifts forward, unhurried, unbothered, carrying its home and its history inside a single coiled form. In all the vastness of the sea, few things have remained as constant as this one. The nautilus has been doing this for more than 500 million years. It began long before the first trees, before vertebrates, before even the first bones. It has survived every extinction the Earth has thrown at life, emerging unchanged while continents cracked and seas evaporated. To see one alive today is to look directly at the design language of the early oceans, a translation of how life first learned to build with geometry. Its shell is the key to its endurance. At first glance, it's just beautiful, a spiral divided into perfect pearly chambers. But that spiral isn't decoration. It's function, refined over eons. Inside, each chamber is a sealed compartment filled with gas. The nautilus controls the pressure in these chambers by pumping fluid in and out through a narrow tube called the siphuncle. By regulating that balance, it adjusts its buoyancy, rising or sinking through the water column with absolute efficiency. It doesn't swim so much as it floats on thought. Every pulse of fluid is a decision made without waste. Modern submarines work on the same principle, yet the Nautilus perfected it 500 million years before we wrote the equations for it. Each chamber represents a stage of its life, added as it grows, sealed off as it moves forward. In that sense, its body is also its biography, a literal record of growth, each partition a memory it no longer needs but refuses to destroy. The living animal occupies only the outermost chamber, but carries all the old ones with it, a moving archive of its own evolution. When it moves, it does so with calm precision. Small tentacles extend from the opening of the shell, feeling the water, reading the space. They're not covered in suckers like those of modern squid or octopus. Instead, they grip by simple adhesion, smooth and silent. The Nautilus has up to 90 of them, arranged around its mouth like delicate instruments. Each one acts independently, a sensory extension tuned to taste and touch. Through them, it hunts, not aggressively, but patiently, feeding on small crustaceans, detritus, and fish that wander too close. Its mouth contains a sharp beak that can crush shells with surprising force. Yet even here, its movements remain slow. It doesn't chase, it waits. Its eyes, primitive compared to its cephalopod relatives, lack the lenses and complex focusing systems of octopus or squid. Instead, they function more like pinhole cameras, open to seawater, capturing light as it enters. The image they form is simple but sufficient. In the deep twilight where it lives, fine detail doesn't matter. Contrast does. Shadows, flashes, movement. These are the languages it understands. Unlike the octopus, which evolved intelligence as its defense, the Nautilus evolved stability. While its relatives became agile thinkers, changing colour and shape to outsmart predators, the Nautilus withdrew into endurance. It built armour and let time flow around it. That choice, to harden instead of adapt behaviourally, made it both ancient and eternal. It's not the smartest of its family, but it's the one that lasted the longest. The shell spiral follows a logarithmic curve, known to mathematicians as the golden ratio, a pattern that recurs in galaxies, hurricanes, and the shape of DNA. Whether by coincidence or inevitability, the Nautilus stumbled into a geometry the universe itself favours. Each coil expands by a consistent proportion, maintaining shape as it grows. No redesign required. The pattern is self-correcting, self-perpetuating, and infinitely scalable. Life used math before math existed. Inside the shell, the animal's body is a study in minimalism. It occupies only the outermost chamber, surrounded by soft tissue, a thin veil of mantle that secretes new layers of shell as it expands. Within that living edge, its organs are arranged in tight order. Gills, stomach, heart, all optimized for balance. Its respiration is slow, its metabolism deliberate. The Nautilus doesn't hurry because nothing in its world demands it. The deep water offers no urgency, no competition for speed. Survival here is not a race, it's endurance. The Nautilus's world is defined by darkness and pressure. It spends its days at depths of several hundred meters, where light fades to faint blue. At night, it rises toward the shallows to feed, following gradients of temperature and prey. This vertical migration, repeated nightly, is one of the ocean's oldest habits. Even as it moves upward, It carries its own ballast, regulating internal pressure to counter the shifting density of seawater. When morning comes, it descends again, returning to the silence below. This rhythm, rise, feed, fall, rest, has continued for hundreds of millions of nights without interruption. To call it a traveller feels appropriate, not because it covers great distances, but because it moves through eras. The nautilus today is nearly identical to the fossils of its ancestors from the Devonian and Carboniferous periods. Its relatives, the ammonites, once filled the seas, their coiled shells littering the ocean floor in spirals of every size. When the great extinction at the end of the Cretaceous wiped out the ammonites along with the dinosaurs, the nautilus endured. It found refuge in deeper waters, cooler and safer, where change arrived slowly. It survived because it knew how to retreat. Its longevity isn't only biological but philosophical, if you could call it that. The nautilus thrives by doing less. It doesn't compete. It doesn't dominate. It simply exists within parameters that never overextend. That's why it survived every upheaval, because it never demanded more than the ocean could give. The same principle that governs its buoyancy governs its existence: equilibrium. When scientists study it, they often use words like living fossil, but that phrase oversimplifies what it represents. It's not trapped in the past. It's adapted to persistence. Evolution didn't stop for it. Evolution arrived at a design that required no further correction. The nautilus isn't a relic. It's a reminder that sometimes progress means finding a form so balanced that the only change needed is patience. Even its reproduction reflects that patience. Unlike many marine creatures that spawn thousands of eggs at once, the nautilus produces few. The female lays her eggs individually, attaching them to rocks or coral, where they take up to a year to hatch. The young emerge as miniature versions of the adults, already encased in tiny spirals, ready to begin their slow journey through depth and time. That long incubation and slow growth mean populations recover gradually, which makes them vulnerable to overfishing. But in an ocean that once moved at geological speed, their rhythm made sense. Modern pressures, however, are faster than any extinction event they've known. In some regions, humans harvest nautilus shells for decoration, their iridescent chambers polished and sold as ornaments. Others are caught for study or as bycatch in traps. Because they mature slowly and reproduce infrequently, even small disturbances can have lasting effects. For a creature that survived asteroids, volcanic winters, and mass extinctions, it's ironic that the biggest threat now comes from curiosity and commerce. Still, they endure. Protected populations continue to drift in the deep Pacific and Indian Oceans. Their presence marks places where the water remains clean, stable, and relatively untouched. The nautilus doesn't tolerate pollution or temperature extremes. It's a natural indicator of the ocean's health. Where it thrives, balance still holds. To observe one alive in its habitat is a rare privilege. Cameras that descend into its realm record something surreal. A small, glowing spiral turning slowly against blackness, tentacles reaching out, retracting, moving with ghostly precision. It's as if the past itself were exploring the present, curious but unchanged. When it moves closer to the lens, its shell reflects the light in bands, revealing centuries condensed into a single curve. That image, soft, silent, exact, encapsulates the logic of survival: evolve just enough and then stop. Its motion is powered by a jet system similar to other cephalopods, water drawn into the mantle cavity, then expelled through a siphon. But unlike the jet bursts of squids, which are built for speed, the Nautilus's pulses are steady and measured. Each push propels it a little further, then it glides, letting momentum carry it. It's the same principle that governs the shark's economy of motion or the jellyfish's pulse: energy used only when necessary. In the deep sea, conservation isn't a virtue, it's law. There's an elegance in how all these old survivors share the same philosophy through different forms. The shark's strength, the crocodile's patience, the nautilus's geometry. All are variations on the theme of endurance through balance. They're reminders that complexity doesn't guarantee longevity, equilibrium does. When the nautilus retracts into its shell, sealing the opening with a leathery hood, it disappears entirely, leaving only the perfect spiral behind. That shape, unchanged through eons, inspired everything from ancient art to modern architecture. Temples, shells of galaxies, even our own mathematical attempts to describe beauty all trace some lineage to this same pattern. The ocean wrote the equation first, and the nautilus carried it forward. As it drifts, you can almost imagine the water remembering each spiral that ever passed this way. The currents have moved millions of them over billions of years, shells rising and falling through the layers, some sinking to become fossils, others still alive, each one a silent chronicle of how the ocean teaches continuity. Sometimes deep divers find their empty shells washed ashore, pale and fragile. To most, they're souvenirs. To the ocean, they're pages torn from an ongoing book. Inside, the chambers remain filled with air, light, and time. The animal is gone, but the design persists, evidence that endurance can outlive the body that conceived it. In the hierarchy of the sea, the nautilus doesn't dominate. It doesn't roar or glow or chase. It exists in quiet defiance of extinction, a geometry that never needed revision. For as long as there are depths cool and stable enough to hold it, it will continue. When future species look back at what survived from our era, they may still find it drifting, unchanged, still charting its slow spiral through eons. And not far from where it moves, deeper still, another survivor glows faintly against the dark. It doesn't carry armor or geometry but light, soft shifting illumination that pulses like breath. It is older than fire, a signal from a world without sun, one of the ocean's most ancient voices of bioluminescence. As we follow it downward, we enter the realm where light itself became a living thing. Deeper still, past the last glimmers of the Nautilus's slow drift, the water grows ancient. Light here isn't light anymore, it's memory. The blue fades to grey, then black, and pressure becomes almost a texture, a presence pressing on every surface. In this quiet, where almost nothing moves quickly and change happens at the pace of stone, something shifts, not a flash, not a dart of speed, but a steady motion, deliberate and out of step with everything else. A large, thick-bodied fish moves through the dark, its fins not flapping like those of other fish, but rotating like slow, patient gears. It looks less like something alive than something remembered. The kilacanth swims through time itself, the last living echo of a world we thought was gone. For most of human history, the kilacanth was a fossil. Its bones were pressed into ancient rock strata, its story assumed finished. Paleontologists studied its remains, tracing the pattern of its fin bones and realizing they resembled primitive limbs. It was one of the first clues to how fish might have moved onto land, how fins became legs, how vertebrates learned to walk. But everyone agreed it was extinct, gone for 65 million years, a casualty of the same event that ended the dinosaurs. The kilacanth was a relic from a world erased. Then, in December 1938, off the coast of South Africa, a fisherman hauled up something strange in his net. It was blue-grey, heavy, about 5 feet long, covered in thick, scaly armour that shimmered metallic in the sun. When marine biologist Marjorie Courtney Latimer saw it, she didn't believe what she was looking at. Its fins moved like jointed arms, its tail symmetrical and ancient in design. She sent drawings to an expert, who nearly fainted when he realised what it was. The kilacanth wasn't extinct at all. It had simply gone deeper, waiting out the ages where no one thought to look. That moment changed our understanding of extinction forever. A species we had written off as history was suddenly alive, real and unchanged. It didn't evolve into something new. It didn't adapt to a new world. It survived by staying exactly the same, holding steady while the rest of life surged forward and fell away. The kilacanth didn't refuse extinction with defiance. It did so by indifference. It simply kept living its quiet, hidden life, untouched by catastrophe. Its body explains how. The kilacanth's most distinctive feature is its lobed fins, fleshy extensions supported by bone, unlike the thin, ray-like fins of most fish. Those lobes move in alternating pairs, almost like the gait of a four-legged animal. When scientists observed this motion on film for the first time, it was like watching the ghost of evolution's first experiment in walking. Each fin rotates independently, providing stability in the water and control in the current. The motion looks strange, but it's a masterpiece of balance, allowing the kilacanth to hover and maneuver in 3 dimensions without effort. It lives deep, typically between 150 and 700 meters, in volcanic caves and steep underwater cliffs where temperatures stay constant. The depth alone protects it, beyond the reach of most predators, beyond the influence of surface change. Down there, time slows. Food is scarce, but the kilacanth's metabolism is slow enough to match. It feeds mostly on cephalopods and small fish, using a specialized joint in its skull to open its mouth wide enough to engulf prey. That joint, a hinge between the front and back of its head, is unique among living vertebrates. It allows the upper part of its skull to lift independently from the rest, creating a sudden suction that pulls food in whole. A simple, brilliant adaptation from an age when efficiency meant survival. Its scales tell another story of endurance. Unlike the smooth or flexible coverings of modern fish, kilacanth scales are thick, diamond-shaped, and built from cosmine, a hard, mineralized tissue that acts as armor. They shimmer faintly in the dark when light touches them, reflecting the faint bioluminescence of other deep-sea creatures. The pattern of those scales matches fossils found in rock layers hundreds of millions of years old. Each scale is like a signature from deep time. The kilacanth's blue coloration, once thought to be random, is actually camouflage. In the deep twilight of its habitat, blue light penetrates the farthest, and by reflecting it, the fish blends into the background, becoming almost invisible. Every aspect of its anatomy serves survival in stillness, the ability to disappear by simply not contrasting with its world. When researchers first dissected one, they found something even more peculiar: a notochord, a gelatinous rod running through its body where most modern vertebrates have hardened spines. This structure is ancient, more like the flexible support rods in early chordates. It allows the kilacanth to flex without snapping under pressure. Its heart, lungs and digestive system retain features of primitive vertebrates, including a vestigial lung that once allowed its ancestors to breathe air. In modern kilacanths, that lung has calcified and no longer functions, a reminder of a time when their relatives lived in shallower oxygen-poor waters. Inside its body are traces of the evolutionary transition that built us, preserved in a creature that never left the water. The rediscovery of the kilacanth was more than a scientific shock. It was a philosophical one. It forced humanity to confront how little we truly know about the ocean. If something as large and ancient as this could remain hidden for so long, what else waits unseen below? It reminded us that the concept of extinction is partly an assumption, a record of absence rather than proof of loss. The ocean doesn't always announce its secrets. In the decades after that first discovery, more kilacanths were found, off the Comoros Islands, then near Indonesia, and later in the Indian Ocean. Each population seemed isolated, separated by thousands of kilometres of open water, yet all nearly identical genetically. The species had survived not as a single relic, but as small scattered communities, tucked into the folds of the Earth's geology. Their distribution hints at a lineage that once covered entire oceans, now reduced to hidden pockets where time forgot to move. Watching one alive, a privilege granted only to a few deep-sea submersible crews, feels like seeing a painting come to life. The fish drifts slowly, fins moving in smooth, alternating patterns, its eyes reflecting light like polished stone. It doesn't startle, doesn't flee, it simply exists, patient and unmoved. In its world, nothing is wasted. Every motion is the minimal requirement to continue. To call it a survivor of extinction is accurate, but incomplete. The kilacanth doesn't merely survive, it endures by embodying balance. It represents a path evolution could have taken but didn't, a branch that found equilibrium early and stayed there. It's not a failed experiment, as scientists once thought, but a successful one that needed no further updates. When everything else raced toward new forms, it stayed in the quiet current of sufficiency. Its reproduction is another reflection of that principle. Kilacanths are ovoviviparous, meaning the eggs develop inside the female and hatch within her before live young are born. The gestation period is extraordinarily long, close to 3 years, one of the longest in the animal kingdom. That slow cycle matches its environment perfectly. In a world where resources are limited and danger minimal, there's no need for haste. Each offspring emerges fully formed, miniature versions of adults, ready for the same slow rhythm of life. That rhythm is central to the kilacanth's survival. Its heart beats slowly, its metabolism drifts in near stasis. It can go weeks without eating. Its energy demands perfectly match to the stillness of its world. It doesn't compete for food, doesn't migrate vast distances. Instead, it remains close to home, caves and cliffs that provide both shelter and feeding ground. Stability, not expansion, is its strategy. The irony is that its greatest threat now comes not from predators or environment, but from us, from curiosity. The very fascination that made it famous also placed it at risk. For years, fishing communities that accidentally caught kilacanths sold them to collectors or scientists. Each discovery cost a life. The slow reproduction rate made population recovery uncertain. Conservation efforts have since reduced the damage, but the tension remains. Our desire to understand can easily outpace the patience of nature. Yet even in the face of that intrusion, the kilacanth remains what it has always been: indifferent. It doesn't adapt to us, doesn't flee from our lights or cameras. It continues its slow circuits through the dark, unaffected by our urgency. To witness that indifference is strangely humbling. The kilacanth doesn't protest or react. It simply continues, as if human history were just another layer of sediment settling above it. Every feature of its biology tells the same story: resilience through minimalism. Its blood has adapted to carry oxygen efficiently at low temperatures and pressures. Its brain, relatively small, is surrounded by a cavity filled mostly with fat, an adaptation for neutral buoyancy and insulation. Even its movement patterns, mapped by tracking tags, show a kind of conservative intelligence. It visits the same shelters repeatedly, returns to the same feeding grounds, and rarely ventures beyond the known. To the kilacanth, repetition is survival. Novelty is unnecessary. In an age where life on Earth accelerates, reproduction cycles shorten, species shift ranges, climates transform, the kilacanth stands as a counterpoint. It's the argument for stillness. It tells us that longevity isn't just about adaptability. Sometimes it's about refusing the rush. Its very existence proves that evolution's goal isn't progress, but persistence. When scientists sequenced its genome, they found something remarkable. Despite its ancient appearance, the kilacanth isn't genetically frozen. It evolves, just incredibly slowly. The rate of mutation in its DNA is one of the slowest known among vertebrates. This doesn't mean it's static, only that its environment has remained stable enough not to demand rapid change. Its body, and the genes behind it, are tuned so precisely to its niche that any alteration would be waste. It's not a fossil come to life. It's an organism that achieved near-perfect equilibrium between form and function. Seeing one in motion drives that home. Its lobed fins move in perfect opposition. Its mouth opens and closes with deliberate rhythm. Its body sways slightly with each stroke. There's no sense of age about it, only continuity. The kilacanth doesn't know it's ancient, doesn't know it's a marvel. It's just alive, exactly as it was meant to be. We like to say it refused extinction, but that's our language, our dramatization. The kilacanth didn't resist anything. It just stayed within the narrow range of conditions that always suited it, and when the world above changed, it sank deeper, out of reach. It didn't fight time, it stepped aside. There's a quiet wisdom in that. In a world obsessed with progress, speed and transformation, the kilacanth reminds us that endurance can come from restraint. It teaches that success doesn't always mean becoming something new. Sometimes it means being enough, and staying that way, no matter how the world rearranges itself. When the submersible lights fade and the cameras rise back toward the surface, the kilacanth remains below, unmoving. The water folds back into blackness, and it drifts onward, one more cycle in its endless pattern. Around it, other creatures pulse, glow, and vanish. Above it, the ocean layers rise through centuries, each filled with the survivors of earlier worlds. The shark, the nautilus, the crocodile, all still here, all carrying different versions of the same ancient endurance. And beyond them, where the deep meets the coldest, darkest trenches of the earth, other forms stir. Not with fins or shells, but with tentacles and light, creatures built for pressure and silence. The ocean, it seems, keeps revealing its old architects one by one. The next of them doesn't swim like a fish or crawl like a crustacean. It hovers, all muscle and mind, a cephalopod built for strategy. The giant squid waits below, and in the deep's unending night, it extends its reach, a living echo of evolution's most mysterious design. The deep fades upward again, the darkness thinning into slow green light. The cold pressure of the abyss loosens its hold, and shapes begin to appear. Drifting particles, silhouettes of fish, the soft glimmer of a current turning over sand. Near the boundary where the seafloor gives way to open blue, something moves with the calm authority of time itself. A smooth shell glides through the water, broad flippers cutting slow, deliberate arcs. A sea turtle moves forward, unhurried, its path invisible but exact. It's been taking this same route longer than the continents have held their shape. The sea turtle is an old traveller in every sense. Its ancestors first appeared more than 100 million years ago, swimming in the same oceans as the last of the dinosaurs. Unlike those giants, the turtle never vanished. It endured the mass extinctions, the cooling and warming of the oceans, the shifts of tides and continents. It carried its house through them all, adjusting, waiting, surviving. The shell that once protected it from prehistoric predators still does the same today, a design tested across epochs and found complete. There's a steadiness to the turtle's movement that feels almost mathematical. Each slow sweep of its flippers pulls it forward without waste. Its body is streamlined, a fusion of ancient armour and modern efficiency. The ribs that once formed a cage fused over evolutionary time into the carapace, the protective dome that defines it. Beneath that dome, lungs expand and contract, pulling in air at the surface before the next long dive. Everything about the turtle is an equation of balance, mass, lift, drag, breath. Nothing moves faster than necessary. Sea turtles spend most of their lives alone, crossing entire oceans with precision that defies explanation. A leatherback hatched on a Caribbean beach may grow to roam the Atlantic, diving thousands of meters deep, then return decades later to the same stretch of sand to nest. Scientists have found magnetic crystals in their brains, structures that act like internal compasses. They sense Earth's magnetic field, reading invisible coordinates with accuracy beyond our instruments. No one taught them this. It's written in their lineage. The same forces that guide migrating birds and salmon pull at the turtle's nervous system, turning the whole planet into a map it can feel. Their migrations are long, sometimes tens of thousands of kilometres. The olive ridley turtle follows circular routes through tropical oceans. The loggerhead crosses from Japan to Baja California. The green turtle rides currents between coral reefs and seagrass meadows. Each species has its own rhythm, shaped by temperature, season, and instinct older than any human boundary. When they surface for air, it's often for only seconds, a brief exchange of gas before they vanish again into the quiet. For hours afterward, they glide weightless in the blue, propelled by memory. Their nesting rituals are among the oldest coordinated events in the animal kingdom. At night, under moonlight, the females crawl ashore, dragging their massive bodies up the same beaches where they hatched. The effort is monumental. Flippers built for swimming struggle against sand, and each metre forward leaves deep grooves behind. They dig with slow persistence, scooping out pits with their rear flippers, shaping them with precision born of repetition. Inside, they deposit dozens, sometimes hundreds of eggs, soft and white, each one a small sphere of possibility. Then they cover the nest, tamping the sand down until no sign remains. The whole process takes hours. When it's over, the female turns toward the surf and lets the waves reclaim her. She'll never see her hatchlings, but her lineage doesn't depend on memory. It depends on return. The eggs incubate under the sand, warmed by the sun. Temperature determines sex. Cooler nests produce males, warmer ones females. A few degrees difference shapes the next generation's balance. The hatchlings develop quietly for weeks, growing eyes and flippers in darkness, until one night they break free together. It's always at night, when the sand cools and the horizon glows faintly with starlight or moonlight. Guided by the brightest direction, once the sea, now often confused by artificial lights, they scramble toward the waves. Most won't make it. Birds, crabs, and fish wait for them. The few that reach the surf are carried into currents that will decide their fates. For decades they'll wander, invisible, until instinct calls them back. The long march never really ends. It only loops. That pattern, leaving, returning, leaving again, is what has kept turtles alive through mass extinction and climate chaos. It's not strategy in the conscious sense, but pattern repetition at planetary scale. The ocean changes slowly, but it always rewards rhythm. Turtles move within that rhythm rather than against it. Their shells bear the marks of that endurance. Growth rings, barnacles, scars from sharks and propellers alike. Each mark tells a story of survival by continuation. Their ancestors weren't all sea dwellers. Some lived in rivers, some on land, some in brackish swamps that blurred the boundary between the two. The great archelon of the late Cretaceous, a sea turtle over 4 meters long, cruised the shallow seas that once covered North America. Its fossilized shell is the size of a small car, its flippers massive. It fed on jellyfish, just as modern leatherbacks do, proving that even then the design worked. When the dinosaurs vanished, turtles like Archelon disappeared too, but others adapted. The lineage splintered, some retreating to land to become tortoises, others remaining in the sea to become the swimmers we know. Evolution pared the design down to essentials and let the survivors carry it forward. That shell, the symbol of their endurance, is both armour and burden. It protects them from predators but limits how fast they can move. Turtles survive by patience, not speed. The shell's bone and keratin layers grow throughout life, forming a mosaic of scutes that overlap like tiles. Beneath it, the lungs sit just below the surface, filling almost the entire upper cavity. That position helps them control buoyancy, shifting slightly to rise or sink. When diving deep, some species collapse their lungs to prevent nitrogen absorption, avoiding decompression sickness, a problem humans still struggle to solve. They learned to master pressure long before we understood it. Different turtles embody different forms of that mastery. The leatherback, the largest, lacks a hard shell entirely. Instead, its back is covered in a flexible layer of skin, an oil-saturated tissue supported by a network of bone plates. This gives it both strength and flexibility, allowing it to dive deeper and tolerate colder waters than any other reptile. Its body temperature remains higher than the surrounding water, maintained by countercurrent heat exchange in its blood vessels, a primitive form of endothermy. It's a reptile with partial control over warmth, an evolutionary bridge between cold and warm-blooded life. The green turtle, smaller but no less ancient, feeds on seagrass and algae, shaping entire ecosystems through its grazing. By trimming the grass beds, it prevents overgrowth, keeping oxygen levels stable and supporting countless other species. It's an ocean gardener, maintaining balance without intent. Where turtles disappear, seagrass beds often decay, showing how even their feeding patterns anchor the health of entire coasts. The loggerhead, with its massive jaws, crushes crustaceans and mollusks. The hawksbill slips into coral reefs, feeding on sponges and keeping reef communities diverse. Each species has its own task, its own ecological function, woven into the broader pattern of marine survival. For over 100 million years, they've done this without pause. They are not relics of a lost world. They are the world's quiet continuity. And yet, for all their endurance, the modern world tests them in new ways. The beaches they need for nesting vanish under development. The light that once guided hatchlings to the sea now lures them inland to their deaths. Ocean temperatures rise, skewing the balance of male and female births. Plastic bags drift like jellyfish, trapping or choking them. Fishing nets catch them unintentionally. Pollution weakens the reefs and grass beds they depend on. It's a cascade of small disruptions, none catastrophic on its own, but together eroding patterns that took eons to perfect. Despite this, turtles still return. They outlast oil spills, cyclones, and the noise of coastal cities. They adapt slowly but persistently. In some places, conservation efforts help restore balance. Protected beaches, artificial lighting limits, fishing gear redesigned to let them escape. Populations once thought lost have begun to climb again. The ocean's memory is long, and where rhythm is restored, life follows. To see a sea turtle up close, gliding through clear water, is to witness calm embodied. It doesn't rush even when pursued. It turns with steady strength, each stroke deliberate. Its eyes, dark and reflective, seem to hold no fear, only presence. It doesn't measure time as we do. Its cycles stretch across decades. A female returning to nest may be 50 years old, repeating the same route she took as a hatchling. Longevity isn't an accident for them, it's design. The idea of the long march suits them, though they don't march. They drift, they crawl, they rise and sink. The march is metaphorical, the slow continuity of a lineage that never broke. From freshwater ponds to open oceans, from fossil record to modern shorelines, turtles have carried their design intact. Even the land tortoises, distant cousins, echo that persistence on solid ground, trading flippers for feet, but keeping the same domed architecture, the same calm rhythm of existence. The Galapagos tortoise, for instance, lives longer than most human civilizations. The same slow metabolism that keeps the sea turtle steady in currents, keeps the land tortoise unmoved by centuries. Time for their family is not an adversary but an element to live within. Their survival isn't dramatic, it's quiet, repetitive, unremarkable in any given moment. But across millions of years, repetition becomes victory. Every hatchling that reaches the sea, every adult that returns to nest is another verse in a song older than mountains. The same moon that lights their path now has lit it for 100 million generations. The same tides that carry them once carried their ancestors through oceans no longer in existence. They are the proof that persistence itself can be an evolutionary weapon. Some scientists have called them living metronomes of the sea, creatures whose migrations and breeding cycles help measure the health of the oceans. When turtles disappear, it means something fundamental in the water's rhythm is off. When they thrive, it means the balance still holds. They are not the ocean's rulers, nor its victims. They are its pulse. Watching one surface for air, its shell breaking the water like a small island, it's hard not to feel how small our own timeline is beside it. A turtle alive today may have hatched when humans were still figuring out flight. It may live to see generations of us come and go. Its shell will record every season, every storm, every shift in the sea's chemistry. And when it finally sinks for the last time, it leaves behind no trace but that pattern, continuing through its offspring and through the shape of the coast it helped shape. The turtle's long march of survival isn't a story of triumph over adversity. It's a story of coexistence with change. It doesn't fight the ocean or dominate it. It flows with it, using rhythm and patience as its tools. In a world where so much life burns fast and disappears, the turtle reminds us what it means to endure slowly, to move at the speed of balance. And somewhere beyond the reefs where the turtles graze, another ancient pattern unfolds. Shadows stir in the deep, slow-moving yet immense, their hearts beating once every few seconds. They rise toward the surface in silence, giants older than the ice that once covered the poles. The whales are coming, carrying the ocean's longest memory on their backs, voices older than language, travelling paths that circle the entire world. The turtles pass over a field of light that isn't sunlight. It comes from below, an expanse of colours that shimmer like breath trapped in stone. What from above looks like a solid reef is, up close, a city built by millions of living architects. The surface swarms with motion, but none of it is hurried. Every inch is occupied by creatures that build, feed, defend, and die, all within structures they've been expanding for over 200 million years. The corals are not plants, not rocks, but colonies of small animals whose bodies shape the skeleton of entire ecosystems. Their cities are alive, and their builders are older than most of what swims above them. Each coral is a community. The visible structure, the stony branches, mounds and labyrinths, is made of calcium carbonate, secreted by countless polyps that live on the surface. Each polyp is only a few millimeters wide, a soft-bodied creature with a ring of tentacles surrounding its mouth. The tentacles reach into the water to catch plankton, but the true power of the coral lies in partnership. Inside its tissues live microscopic algae called zooxanthellae. These algae photosynthesize, turning sunlight into sugar, and share the energy with their coral hosts. In exchange, the coral provides shelter and carbon dioxide. Together they form one of evolution's most successful collaborations, an alliance between animal and plant that turned empty ocean shelves into thriving habitats. Over millions of years, as coral colonies grow and die, their skeletons stack atop one another, rising toward the surface. Each generation builds on the bones of the last. What begins as a thin crust on rock becomes a reef, the size of continents. The Great Barrier Reef stretches for over 2,000 kilometres, large enough to be seen from space, yet every centimetre of it is the accumulated work of animals smaller than a grain of rice. This is how life writes permanence, not through individuals, but through repetition across time. In the shallows, where light filters down in beams, the reef feels almost like a metropolis. The polyps are the unseen workers, their bodies hidden by limestone walls, while above and between them moves an entire economy of species. Fish weave through coral towers, each niche supporting something specific. Butterfly fish pick parasites from coral heads. Parrotfish grind the limestone into sand with their beaks. Cleaner wrasses attend to larger predators like surgeons, shrimp hide in crevices, sea urchins scrape algae from stone. Every layer of the reef feeds or shelters another. Corals evolved during the Triassic period, in the wake of a mass extinction that had erased most marine life. When the oceans calmed and temperatures stabilized, they returned, rebuilding from fragments. Their ancestors, the rugose and tabulate corals, had flourished in Paleozoic seas long before, but those lineages died out. The modern corals, scleractinians, took their place, refining the art of skeleton building. They spread across tropical shallows, growing wherever sunlight could reach, turning chemical exchange into architecture. Their growth rates vary. Some add only a few millimeters per year, others centimeters, but across centuries those increments become mountains. The skeletons they leave behind form limestone deposits that record ocean history. Scientists drill cores from reefs and read them like tree rings. Each layer reveals data, temperature, salinity, carbon levels, even ancient storms. The coral city isn't just a habitat, it's a geological memory bank. Its walls remember every shift in the planet's rhythm. Coral polyps live simple lives. They extend tentacles at night to feed, retract during the day, maintain the balance of calcium and carbonate ions around their skeletons, and divide when it's time to grow. Reproduction happens both sexually and asexually. Entire reefs can spawn in synchrony, a night when millions of polyps release eggs and sperm into the water, a slow snowfall of life drifting upward. The timing is triggered by moonlight and temperature, so precise that even a single degree or an artificial glow can disrupt it. Within hours, the surface becomes a living soup of possibilities. Some of those larvae settle on rock and begin new colonies. Others drift for weeks, carried by currents until they find the right combination of depth and light. Most die. A few begin building again. That pattern, growth, decay, renewal, has been the reef's secret for ages. Every structure is temporary at the level of individuals but eternal in the collective. The city lives because its builders never stop replacing themselves. No one coral lives for centuries, the colony does. Time, for them, is measured in continuity rather than lifespan. The relationship with zooxanthellae defines coral success, but it's also its greatest vulnerability. The algae require a narrow range of conditions: stable temperature, clear water, consistent light. When the water warms or pollution clouds it, the partnership falters. The coral expels the algae, turning white in the process. This bleaching is not immediate death, but starvation. Without their symbiotic partners, corals lose their main energy source. Some recover when conditions improve, many don't. Whole reefs can fade in months. Their builders still alive but unable to grow. The skeletons remain, barren monuments of what once thrived. For most of Earth's history, bleaching was rare, triggered only by volcanic winters or local changes. Now it happens regularly, as ocean temperatures rise and currents shift. Reefs from the Caribbean to the Pacific have suffered mass events in recent decades. Some recover, others crumble, replaced by algae or barren rock. It's not that the coral design failed, it's that the speed of change exceeded its rhythm. The builders can't rebuild fast enough when the foundation itself keeps moving. Yet even amid collapse, there are signs of resilience. Some coral species tolerate higher temperatures, some host different algae more suited to warmth, some adapt to murkier water. In certain regions, hybrid reefs form, slow mixtures of old and new species finding balance in disturbed environments. The builders don't surrender easily. Evolution still works here, just at scales too slow for us to notice directly. Within the living reef, diversity is astonishing. Coral shapes vary, branching like trees, forming domes, plates, or thin encrusting layers. Each shape responds to light, current, and sediment flow. Branching corals grow fast but break easily. Massive boulders grow slow but endure storms. Together they form mosaics that absorb wave energy, protecting coastlines from erosion. Entire human cities owe their safety to coral cities beneath them. Beyond structure, the reef's chemical exchanges sustain oceans far beyond its boundaries. The coral polyps recycle carbon, nitrogen, and phosphorus, anchoring nutrients that would otherwise drift away. Plankton blooms feed fish that feed predators, connecting the reef to open water ecosystems hundreds of kilometres away. The reef is both a habitat and an engine, powering the circulation of life through invisible chemical loops. When divers descend into these places, what they see is only the surface of an immense machine. The colours, the pinks, greens, oranges and blues, come not from the corals themselves, but from the algae inside them and the light scattering through shallow water. Under ultraviolet light, corals fluoresce, emitting their own glow in patterns that may serve as protection or communication. To human eyes, it looks like a celebration, but to the corals, it's function, light management, photosynthetic efficiency, chemical defense. Even beauty in the reef is utilitarian. Some scientists refer to reefs as the rainforests of the sea. The comparison fits, but it misses something essential. Forests grow from soil, reefs build their own ground. Every coral structure is both organism and environment. They create the very world they need to survive. Few systems in nature are that self-sustaining. When you look closely at a single coral polyp, it doesn't appear remarkable. It's soft, translucent and fragile, easily damaged by touch. Yet multiplied by billions, their collective architecture can withstand hurricanes. When waves crash against a reef, the energy disperses across the irregular surface, absorbed and redirected by the coral's complexity. It's a form of biological engineering beyond anything human design has achieved. Reefs build not for strength, but for distribution, a principle that keeps them standing even under constant assault. The builders themselves rarely move far. Each polyp is rooted in place, connected by thin tissues that allow nutrient sharing within the colony. Communication occurs chemically. When one section senses stress, heat, acidity, or damage, it can trigger responses in neighbours. The reef acts as a distributed organism, individual minds replaced by networked reaction. In that sense, it resembles the neural networks humans are only beginning to model in technology. The coral has been practicing decentralized intelligence since before mammals existed. Predators visit too. Parrotfish bite off chunks of coral to reach the polyps within, contributing unintentionally to the reef's growth by producing sand from the ground limestone. Crown-of-thorns starfish can devastate entire reefs, feeding on living tissue, yet even these outbreaks are part of a larger cycle. When populations of one species surge, others follow to balance them. Over geological timescales, no disturbance remains permanent. What makes reefs truly ancient isn't just their age, but their role as anchors of continuity. Throughout Earth's history, corals have come and gone, their remains forming the limestone backbones of continents. The white cliffs of Dover, the mountains of the Alps, even parts of the Himalayas, all were once coral reefs under ancient seas. What began as microscopic labour at the bottom of warm oceans became the foundation of land. When corals build, they don't know they're shaping the future continents. They simply follow chemistry, and chemistry writes geology. Modern coral cities are smaller than those ancient expanses, but they remain the same kind of civilization, silent, patient, cumulative. They don't expand in human time, they grow in the scale of tides and centuries. To them, a storm is an inconvenience, not a crisis. A generation is a blink. The city continues as long as the partnership between coral and algae holds. That partnership, fragile as it is, still persists in most of the tropical seas. Even where bleaching events have stripped reefs bare, new growth begins at the edges, microscopic settlers attaching themselves to the bones of the old. Life, once established in a pattern, tends to find its way back. In the Red Sea, corals have adapted to high temperatures that would kill others. In certain Pacific atolls, reefs have shifted species composition but maintained structure. The architecture changes its materials but not its purpose. What we see when we look at a reef is not permanence but process. Creation and decay happening at once. Every coral colony is dying and rebuilding simultaneously. The skeleton grows as the living tissue at the surface expands. Behind it, older layers erode and dissolve. It's a biological paradox. To endure, it must constantly fall apart. Perhaps that's what all long-lived systems learn. Survival is a balance between growth and loss. As the sun moves westward, the reef's light changes. The polyps retract. Fish retreat into crevices. Nocturnal hunters emerge. Octopuses slide from holes. Crabs scuttle between coral heads. Eels weave like shadows through branches. The city doesn't sleep. It shifts roles. Every hour, every tide, its inhabitants exchange duties. Somewhere above, a wave breaks, scattering light into the water like shattered glass. The reflection ripples across the coral below, a reminder that everything here depends on what happens far beyond sight. The reef's builders don't know the surface world, but they feel its influence. The heat of the sun, the clarity of the water, the balance of the chemistry that reaches them. They adapt to every change slowly, without panic, always building forward, one calcium crystal at a time. It's strange to think that something so ancient and intricate owes its existence to creatures that never move more than a few millimeters. But that's the lesson the reef teaches. Greatness doesn't require motion. Sometimes it's the stillest things that construct the world. And beyond the reefs, past the shallow platforms where corals end and the drop-off begins, another kind of life takes over. One that doesn't build, but hunts. In the dim zone between light and darkness, long arms stretch through the water, reaching with intelligence older than bones. The cephalopods are waiting, creatures that learn to master not permanence but change, the shapeshifters of the sea, heirs to an ancient line that began alongside the corals and never left the depths. Beyond the reef, the seafloor falls away. The bright patterns of coral fade into shadow, replaced by long, open stretches of blue that deepen to grey. It's quieter here. The sound of snapping shrimp and grazing fish fades, until there's only the low pulse of the current against stone. The reef ends abruptly, and in its place begins another world, one ruled not by builders but by tacticians. Shapes emerge, then disappear, reappearing somewhere else as if the water itself were rearranging its mind. Among these shadows move the cephalopods, the silent hunters of the deep past, creatures that have rewritten what it means to be alive in the ocean for 500 million years. Their lineage began long before the first coral cities rose, when the seas were simpler and life was still deciding on its basic blueprints. Around 500 million years ago, during the Cambrian explosion, the first cephalopods appeared, soft-bodied mollusks with external shells that helped them float and maneuver. They were among the earliest animals to develop jet propulsion, expelling water through a siphon to move backward in quick bursts. It was a simple idea: push water one way, move the other. But it changed everything. For the first time, life in the sea could move not just by drifting or crawling, but by choice. The ocean, once ruled by passive creatures, now had predators that could pursue. These early cephalopods were armoured. Their shells, often coiled or straight, protected them from the primitive fish and arthropods that filled the Paleozoic seas. The nautiloids, distant ancestors of the modern nautilus, dominated for millions of years. They came in many shapes: long cones, tight spirals, elaborate curves, each representing a different approach to balance and buoyancy. Their shells contained chambers, gas-filled compartments that controlled depth through the same principle the nautilus still uses today. With this innovation, they became the first masters of the open water, roaming freely through the ancient oceans. But evolution doesn't stay still. As new predators emerged, armoured fish, giant sea scorpions, the first sharks, the cephalopods began to trade armour for agility. The external shell, once a shield, became a burden. Over millions of years, some lineages internalised it, shrinking it to a thin structure inside the body. Others lost it completely. What they gained instead was flexibility, speed, and intelligence. By the time dinosaurs appeared, the oceans were filled with squids and octopuses that bore almost no resemblance to their shelled ancestors. They had discovered a new kind of survival, one based not on endurance, but on adaptation through awareness. The octopus, the cuttlefish, and the squid each represent different answers to the same evolutionary question. The octopus embraced stealth and manipulation. With 8 arms lined with suction cups, it became an expert at exploration. The cuttlefish mastered communication, turning its skin into a display system capable of language through colour. The squid chose speed and coordination, evolving streamlined bodies and powerful jets to move through open water in coordinated groups. Each of them inherited the same nervous system structure, large, distributed, and remarkably complex. Among invertebrates, cephalopods have the most sophisticated brains on Earth. Some species have more neurons in their arms than in their central brains, allowing each limb to act independently while still part of the whole. It's not intelligence in the human sense. It's something stranger, a decentralized consciousness where perception and action are nearly simultaneous. Their intelligence wasn't planned. It emerged as a necessity of vulnerability. When you have no shell and live in a world of predators, the only way to survive is to anticipate, react, and outthink everything around you. Over millions of years, cephalopods refined that skill into art. They can change colour, texture, and shape in less than a second. Muscles under their skin expand or contract to reflect light differently, mimicking rocks, sand, coral, or open water. Some species even create dynamic illusions, shifting patterns that confuse prey and predators alike. A cuttlefish can flash one pattern to distract and another to approach, controlling its body like a living screen. Fossils show that this intelligence is ancient. In the Jurassic and Cretaceous seas, the ammonites, close relatives of modern squids and nautiluses, filled the oceans with spiraled shells that rivaled corals in abundance. Their coiled designs varied endlessly, some tight and simple, others wild and ornate, evidence of evolutionary experimentation. They were hunters and scavengers, their soft bodies hidden within chambers of shell. When the asteroid struck 66 million years ago, the ammonites vanished, unable to survive the sudden cooling and acidification that followed. Yet their cousins without shells, the squids and octopuses, endured. The survivors were the ones who had already abandoned permanence for flexibility. Modern cephalopods carry that legacy in their every movement. The squid, with its streamlined body and fins, glides like a machine tuned for efficiency. Its tentacles can strike in a fraction of a second, lined with suction cups and hooks that hold fast to prey. Its eyes, nearly as complex as a human's, evolved independently. A case of convergent evolution that arrived at the same solution, to seeing clearly underwater. Some deep-sea squids have eyes the size of dinner plates, capable of detecting faint bioluminescence from great distances. In the pitch-black depths, that sensitivity means survival. The octopus, meanwhile, thrives in the shallows and on the seafloor, a master of hiding and problem-solving. It can squeeze through gaps no larger than its beak, unscrew jars and open shells with calculated precision. In laboratory studies, they recognize individual humans, navigate mazes, and learn through observation. Some scientists hesitate to call this intelligence in the way we define it, but whatever it is, it's deliberate, measurable, and ancient. A creature that can plan ambushes and escape from enclosures isn't operating on instinct alone. The cuttlefish, less famous but equally remarkable, adds another layer: communication. Its skin can produce waves of colour that move across its body like language. Some patterns are warnings, others invitations, some even mimic the movement of water plants to break outlines and avoid detection. During courtship, males display rapidly shifting hues to signal readiness, while hiding those same signals from rival males approaching from behind. It's a complex social behaviour, made more impressive by the fact that cephalopods live only a few years. They evolve fast because their lives are short. Every generation is a new experiment in refinement. If the coral reef is a city of builders, the world of cephalopods is one of strategists. Their existence is defined by motion and awareness. They read the water through touch and vibration, see polarization patterns invisible to most other eyes, and respond faster than their predators can act. Their blood, based on copper rather than iron, carries oxygen efficiently in cold, low-oxygen environments. Their blue blood and 3 hearts, 2 for the gills and 1 for the body, circulate a rhythm that's ancient and efficient. When they rest, which isn't often, their colour pulses gently in sync with their heartbeat, as if thought and circulation are one. The ocean they inhabit has always rewarded adaptability. During mass extinctions, cephalopods shifted habitats, adjusted reproductive strategies, or evolved new body plans. Some grew to enormous sizes, like the colossal squid of the Southern Ocean, with eyes large enough to see predators like sperm whales approaching from hundreds of meters away. Others became tiny, transparent or bioluminescent, adapting to niches that larger animals ignored. The deep sea, which crushes most life under pressure, became their refuge. There, they drift like shadows, their bodies elastic, their movements whisper quiet. What sets them apart from other survivors of deep time is their constant reinvention. Sharks perfected one design and stayed with it. Corals built continuity through repetition. Turtles carried armour and patience. Cephalopods evolved through transformation. Their story isn't one of stability, but of continual adaptation. They learn to survive not by staying the same, but by always being ready to change. This flexibility extends to their life cycles. Many species reproduce only once. After mating, the female lays eggs and guards them until she dies. It's a short life, but within it, every instinct and action is directed toward ensuring the next generation. The male transfers spermatophores, packets of sperm, with a specialized arm, sometimes losing it in the process. The female cleans and aerates the eggs, refusing to eat, her body slowly breaking down until the hatchlings emerge. Life in this lineage burns fast, but it never fails to restart. The silence of their death matches the silence of their hunt. In the fossil record, we find their signatures everywhere. Ink sacs fossilized intact, shells from vanished species, imprints of tentacles. In some ancient limestone deposits, the remains of an ammonite still contain traces of ink, black as if it were drawn yesterday. That ink, a mixture of melanin and other compounds, has remained chemically similar for hundreds of millions of years. Even the tools of their defense have endured unchanged. When threatened, a modern squid or octopus releases a cloud of ink that acts both as a smokescreen and as a chemical deterrent, confusing predators' senses. The same tactic worked when trilobites roamed the sea floor. To see one alive in the deep ocean today is to glimpse that continuity. The lights of a submersible reveal a flash of shape, an eye, an arm, a pulse of motion, then it's gone. The body reforms somewhere else as if the water itself folded around it. Its camouflage isn't invisibility in the magical sense. It's mastery of physics, light, texture, shadow, all recalculated instantly. In a medium where visibility means vulnerability, they've made the act of being seen optional. When people first studied cephalopods closely, they were often unnerved. These were not simple animals. Their intelligence seemed familiar in a way that challenged our assumptions about consciousness. They could solve problems, use tools, even play. But their minds evolved separately from ours, along a completely different path. They are the closest thing we have to an alien intelligence on Earth. A different experiment in awareness that started in the same ocean and reached a similar result. In mythology, cephalopods have always occupied the space between fear and fascination. Sailors told stories of krakens large enough to drag ships under, their tentacles rising like trees from the water. Those legends likely grew from encounters with giant squids washed ashore or seen briefly on the surface. Even today, the sight of a living giant squid is rare. They spend their lives far below human reach, feeding on deep-sea fish, hunted by whales, and leaving behind only scars and stories. But the truth behind the myth is even stranger, that such creatures have existed largely unchanged since long before we could imagine them. Cephalopods remind us that survival isn't just endurance, but imagination. The ability of life to invent new ways to exist when the old ones fail. Their legacy stretches from the first shell-bearing ancestors that drifted through Cambrian seas to the modern octopus solving puzzles in a tank. Each stage represents the same principle expressed differently: motion guided by thought, awareness as a tool for adaptation, and still they evolve. In warmer waters, species expand ranges. In polluted shallows, they change diets. In areas of overfishing, their numbers increase, filling ecological gaps left by declining fish populations. Where others falter, they find opportunity. The silent hunters remain flexible, unburdened by rigidity, unafraid of reinvention. Beneath all that change, though, is something constant: their link to deep time. Every movement of a modern squid carries echoes of those first nautiloids propelling themselves through ancient seas. Every flash of an octopus's skin recalls the long evolutionary conversation between predator and prey. They are not ghosts of the past. They are the past still thinking. If the coral reefs are the ocean's architecture and the sharks its regulators, then the cephalopods are its artists, the ones who turn survival into creativity. They live short lives, but within those brief spans they condense millions of years of adaptation into action. Every hunt, every escape, every display of light across their skin is evolution performing in real time. And somewhere in the deeper water, below the range of light where their cousins still roam, another lineage continues that art of endurance differently. It doesn't hunt, doesn't change shape, doesn't flash light. It drifts unseen, an armoured ghost from the dawn of time. The crustaceans, the survivors in shells, bearing designs as old as the ocean floor itself. They scuttle through the sediment, their claws echoing the first grasp of movement, their bodies carrying the history of a world built from exoskeleton and persistence. Below the moving shadows of the cephalopods, deeper still, where the light fades and the water cools to a steady calm, the sea floor is covered in the remains of creatures that once wore armour. Every surface bears fragments, plates, shells, ridges of stone-like exoskeletons left behind by lives that ended hundreds of millions of years ago. The world's first engineers of protection evolved here, long before the bones of vertebrates ever hardened. They learned that in the ocean, to endure meant to build a wall around the self. The story of armour in the sea begins with the trilobites. For more than 250 million years, they dominated the ocean floor, crawling, burrowing, scavenging and filtering. Their bodies were divided into three parts: head, thorax, tail, each protected by interlocking plates that allowed flexibility and defence. They were among the earliest animals with complex eyes, each made up of dozens, sometimes hundreds of calcite lenses. Through them, they saw the dim green light of ancient oceans long before fish existed. Those eyes, preserved in fossils, still refract light today when you hold them under a beam. A small miracle of endurance, vision turned to stone but never lost. Trilobites appeared around 520 million years ago and vanished in the Permian extinction, the largest die-off in Earth's history. Yet in that time, they evolved into thousands of species mastering nearly every marine environment. Some swam freely, others burrowed, some were spined and defensive, others smooth and armoured. Their diversity tells the story of early evolution learning to experiment with form. The trilobite exoskeleton, made of chitin and calcite, was both shield and skeleton, the framework of an idea that life would refine for hundreds of millions of years. When the trilobites disappeared, their design didn't vanish. It was inherited, reinterpreted, passed down in the language of evolution to new kinds of creatures. The crustaceans, crabs, lobsters, shrimp, continued the tradition, turning armour into architecture. The crab in particular became the most perfect expression of that idea. Across evolutionary history, multiple unrelated lineages have independently evolved crab-like shapes. Biologists call this process carcinization, nature's strange tendency to reinvent the crab. Something about the form works too well to stay rare. The body of a crab is a lesson in efficiency. The wide, flat carapace protects vital organs while allowing movement through tight spaces. The claws serve both as tools and weapons, capable of delicate manipulation and crushing force. The eyes, mounted on stalks, provide panoramic vision, and the legs are built for sideways motion, faster, more stable, and better for sudden retreats. In an ecosystem of shifting sands and hidden predators, the crab's shape offers balance between strength and agility. That design didn't appear all at once. Early crustaceans, like the anomalocarids of the Cambrian, were larger, stranger, more primitive. They hunted in open water with grasping appendages and segmented bodies. Over time, as predators grew faster and the seafloor became more crowded, natural selection favoured smaller, tougher forms. Exoskeletons thickened, limbs specialised, and by the Jurassic period recognisable crabs scuttled through the shallows. Since then, they've changed little. The ocean keeps trying new variations, but the classic crab form remains one of its most successful inventions. Crabs are not solitary relics, but part of an enormous lineage that includes lobsters, shrimp, krill, and barnacles. All of them share the same core principle: the body as fortress. Their exoskeletons are made of chitin reinforced with calcium carbonate, light yet resilient. When a crab grows, it must shed this armour, a process called molting. During molting, it's vulnerable, its new shell still soft and translucent. It hides, waiting for the exoskeleton to harden again. This cycle of shedding and renewal repeats throughout its life. Growth, for a crab, means periodic vulnerability. It cannot expand without first losing its protection. The process is risky, but it's also the secret to their persistence. The ability to rebuild oneself after shedding what no longer fits is an evolutionary masterpiece. The trilobites couldn't do this. Their shells were rigid, limiting flexibility. Crabs learned how to grow within constraint, how to make armour temporary. They are the paradox of strength through fragility, each molt a reminder that adaptation demands exposure. In coral reefs, mangroves, estuaries, and deep-sea vents, crabs occupy nearly every ecological role. Some filter water, others scavenge, some hunt. The giant Japanese spider crab, with a leg span that can reach 4 meters, patrols the deep slopes off Japan's coast, moving slowly but confidently. At the other end of the scale, tiny pea crabs live inside the shells of clams or within the bodies of sea cucumbers, sharing food and shelter in a delicate symbiosis. Between these extremes lies a vast spectrum of forms, each fine-tuned for its niche. Their armour gives them an advantage, but it's not impenetrable. Predators have evolved ways to exploit weakness. Fish with strong jaws, octopuses that pry open shells, and even other crabs that specialise in crushing their kin. In response, some crabs develop elaborate defences: thicker shells, sharper claws, camouflage, or toxic symbioses. The decorator crab covers itself with sponges and algae, creating a living disguise that grows with it. Others blend perfectly with sand or coral. The crab's greatest defence is its adaptability, a constant conversation between form and environment. Traces of that conversation stretch back in the fossil record. Entire layers of limestone and shale are filled with crab impressions, claws fossilised mid-motion, shells turned to mineral. Some species appear almost identical to their modern descendants. Others look like prototypes that nature discarded. The persistence of the crab form across eras shows that once evolution finds balance, it tends to return to it again and again. Even today, scientists discover new crab-like species that aren't technically crabs at all. False crabs, squat lobsters, hermits that outgrew their borrowed shells and hardened their bodies instead. Carcinization continues as a recurring theme in life's story, an echo of the trilobite's first idea carried forward. The armour itself is not just protection, but chemical ingenuity. Chitin, the main component of crustacean shells, is a polysaccharide, a sugar polymer that's light, flexible, and remarkably strong for its weight. Humans now extract it from discarded shells to make biodegradable plastics, medical sutures, and water filters. The same substance that once shielded trilobites and crabs from predation may one day help us replace our own artificial armour. The ocean has always been a quiet laboratory of solutions, long before we learned to copy them. Some crabs have even moved beyond the sea. Hermit crabs live part of their lives on land, carrying borrowed shells for protection. Coconut crabs, their largest terrestrial relatives, have abandoned shells altogether, growing thick exoskeletons and lungs adapted for air. They climb trees, steal fruit, and sometimes even scavenge carrion, their claws strong enough to crack coconuts, a task no other animal performs. They are reminders that evolution doesn't confine its inventions, it exports them. The architecture of armour that began underwater now walks on beaches and climbs into forests. Despite their variety, crabs share one unifying behaviour: opportunism. They are recyclers of the ocean. Nothing is wasted around them. They consume leftovers from hunts, detritus, even dead members of their own kind. By cleaning the seafloor, they maintain the balance between life and decay. This role is ancient. Trilobites likely played a similar part in their ecosystems. The armoured scavenger is one of nature's oldest professions. In their world, communication is silent but constant. Crabs signal through movement, raising claws, drumming on the sand, vibrating their shells to send messages through the water. Some species wave in rhythmic patterns to attract mates or warn rivals. Others release pheromones to coordinate molting or spawning. Their social language is subtle but effective, encoded in gesture and timing. In that sense, they resemble the coral polyps, individuals acting collectively, each move adding to a larger rhythm of the ecosystem. What's remarkable is how this design of armour and adaptability has persisted across so many mass extinctions. When the Permian seas boiled, when the Cretaceous skies darkened, when the ice ages froze the coasts, crustaceans endured. They migrated, diversified, and rebuilt. Their ability to exploit new environments, to rebuild exoskeletons, and to occupy nearly every ecological role made them unkillable by circumstance. Like the shark or the turtle, they represent one of evolution's recurring truths. Balance outlasts brilliance. The trilobites, though long gone, remain part of this continuum. Their fossils still lie in the strata of ancient seabeds. Their shells turn to stone, but their design, alive in modern crabs. The armour they pioneered has never disappeared. It has only changed hands. When you hold a trilobite fossil and a crab shell side by side, the connection is obvious. The segmentation, the symmetry, the logic of defence as identity. It's the same blueprint written in different eras. In the deep sea, crabs continue to explore new forms. Some species live around hydrothermal vents, where superheated water rich in minerals bursts from the seafloor. There, in total darkness, surrounded by temperatures that would kill most life, the yeti crabs thrive. Their pale bodies are covered in fine hairs that host bacteria, which convert chemicals from the vents into food. The crab tends its microbial garden like a farmer, waving its arms through the water to feed the bacteria with minerals. It's one of the strangest partnerships in the ocean, an armoured animal that cultivates life on its own body to survive in a place without sunlight. Others live in polar waters, beneath ice sheets, moving slowly in the cold, their metabolisms reduced to near stillness. Some inhabit depths where pressure would crush most bones, their exoskeletons adapted to resist collapse. The deeper we look, the more forms we find, each a variation on the same enduring principle. In every case, the story is the same: protection, adaptation, persistence. The armour of ages isn't just about shells or claws, it's about the philosophy of survival written into biology. The idea that to last, one must learn to endure impact and then rebuild. Crabs, lobsters, trilobites, they're all practitioners of that philosophy. When a crab walks across the seafloor, it leaves tracks that last only moments before the current erases them. But the design of its body has left tracks across time, embedded in rock, replicated in form after form. Its existence bridges eras. It connects the first armoured explorers of the Cambrian with the scavengers cleaning coral reefs today. It reminds us that progress in nature is often circular, that success repeats itself until the conditions change. As the light fades deeper into the sea, the armoured creatures become fewer, replaced by softer, translucent bodies that drift upward toward the open water. The crab retreats to the rocks, disappearing beneath ledges as the current strengthens. Above it, something vast passes, its shadow blotting out the last traces of light from above. The shape moves with the slow gravity of extinction's memory, a giant that once ruled the ocean with teeth the size of knives. The balance shifts again, and the story of armour gives way to the story of power, of hunters so large that even time seemed to bend around them. The ancient echo of Megalodon begins to rise. The shadow that passes above the crabs is not just an animal, but a memory of power. Its form no longer cuts through the water, yet the shape remains carved into the collective memory of the sea. Even now, millions of years after its last hunt, the presence of that predator still lingers in the behaviour of everything that swims. The Megalodon, the ancient giant of sharks, ruled the oceans for millions of years, and though its body is gone, its echo persists in every smaller hunter that followed. To understand what Megalodon was, it helps to see the ocean as it once was. Around 23 million years ago, during the Miocene, the seas were warmer, the coasts broader, and life abundant. The continents had nearly reached their modern positions, and currents circled the globe in complex patterns that distributed heat evenly. Whales were emerging as dominant marine mammals, filling niches once occupied by reptiles. The oceans were crowded with large creatures: sea cows, seals, dolphins, and early baleen whales. It was a time of plenty, and where there is plenty, there are predators to balance it. The Megalodon was not a mythic beast, but a biological inevitability, the ocean's apex refinement of predatory design. It belonged to the same lineage as today's great white shark, though larger and broader, with teeth over 15 centimetres long and a bite force unmatched by any known animal. Its jaws could open wide enough to swallow a person whole without effort. Estimates of its length vary, but the largest individuals likely exceeded 18 metres, longer than a city bus, heavier than a jet. Yet its size was not what made it terrifying. It was the intelligence of efficiency, the way its anatomy reflected the ocean's logic perfectly. Its skeleton, like that of all sharks, was made of cartilage rather than bone, light, flexible, self-repairing. This allowed the Megalodon to move with surprising speed for its mass. Its muscles attached directly to dense layers of connective tissue that acted like springs, storing and releasing energy with each movement. Its tail, crescent-shaped and powerful, could drive its bulk forward in sudden bursts. Every part of it was designed for precision. The massive head, conical and hydrodynamic, allowed for frontal attacks at high velocity. The eyes, positioned slightly forward, gave a limited but effective sense of depth, crucial for striking prey that could weigh several tons. The megalodon's prey were not fish but whales. Fossil evidence shows bite marks on ancient whale bones, deep semicircular gouges where teeth the size of knives once sank in. Some whale vertebrae still bear those scars, half healed before death, proof that these giants met and fought more than once. Megalodon didn't chase its prey across open water. It ambushed, striking from below or behind, targeting soft tissue and fins first to disable movement. Once the whale was crippled, it circled, waiting for exhaustion to finish the hunt. Predation at that scale was not chaos but calculation. Its teeth, the most enduring relics of its existence, are scattered across seabeds worldwide. Each one is triangular, serrated, and perfectly adapted for slicing through flesh and bone. Sharks lose and replace teeth throughout their lives, so a single megalodon could shed tens of thousands over decades. These teeth, fossilized in mineral, are all that remains of the greatest marine predator the planet has known. They're found embedded in cliffs, dredged from riverbeds, sold as curiosities, each as a shard of history sharp enough to still cut skin if handled carelessly. The oceans megalodon ruled were dynamic and full of competition. Smaller sharks followed in its wake, scavenging leftovers. Early orcas and other toothed whales hunted in pods, developing social strategies that allowed them to defend against even enormous predators. It was an evolutionary arms race, strength against coordination, size against intelligence. For millions of years, balance held. Then the climate shifted. Around 3 million years ago, ocean temperatures began to cool as the planet entered a cycle of glaciation. Ice sheets expanded, sea levels fell, and coastal nurseries where megalodon pups had once grown disappeared. Many of the warm water whales it hunted migrated or evolved into species that could tolerate colder seas. The great predator found itself without stable feeding grounds. Its size, once an advantage, became a liability in a world with fewer large prey and less stable climates. Energy demands outstripped supply. One by one, the giants disappeared, but extinction doesn't erase influence. The smaller sharks that survived inherited an ocean shaped by megalodon's reign. The great white shark, one of its likely descendants or close relatives, emerged as the new apex predator, occupying the same ecological role on a smaller scale. Its behaviour mirrors the patterns established by its ancestor: stealth, ambush, precision. The modern great white's hunting techniques, from striking seals at the surface to breaching attacks, may be echoes of strategies refined in the age of megalodon. To the ocean, size is both triumph and risk. The larger a creature grows, the narrower its margin for error. Megalodon's extinction underscores that truth. The same evolutionary path that granted dominance also created dependency. When the food web thinned, the smaller, faster, and more adaptable survived. Still, the idea of megalodon endures because it represents something elemental about the sea, the moment when raw power was perfectly aligned with purpose. In a way, megalodon was the culmination of a process that began with the first jawed fish. For hundreds of millions of years, evolution refined the art of predation, from the armoured placoderms of the Devonian to the streamlined sharks of the Jurassic. By the Miocene, the blueprint was complete. Cartilage for flexibility, teeth for regeneration, a circulatory system tuned for motion, senses designed to detect electric fields and vibrations. Megalodon was the peak expression of that lineage, the ocean's ultimate convergence of design and demand. Its disappearance reshaped marine ecosystems. Without it, populations of large whales likely increased, allowing new species to evolve. Orcas diversified, filling the role of apex predator with intelligence rather than sheer size. Smaller sharks spread into habitats once dominated by their giant kin. The balance shifted, but the structure remained. The ocean always replaces its rulers. It never leaves a throne empty for long. Still, traces of megalodon linger beyond fossils. In the behaviour of whales today, there's evidence of inherited fear. Some species give birth in shallow coastal waters where large predators cannot follow easily, a strategy that may date back to the time of Megalodon. The faint echo of that ancient threat still guides migrations millions of years later. The memory of being hunted doesn't vanish easily from evolution's record. The fascination humans feel for Megalodon has less to do with its biology than with what it represents. It's the embodiment of scale, life reaching its physical limits. We live in a world where size often equates to dominance, and Megalodon was the ocean's perfect metaphor for that idea. Yet its extinction is also a warning that dominance is temporary, that adaptation matters more than supremacy. Even the greatest predator can vanish when the environment it controls begins to shift beneath it. In studying its remains, scientists learn more than anatomy. The isotopic composition of its teeth reveals migratory patterns, suggesting it travelled long distances between breeding and feeding grounds. Its range likely spanned every temperate ocean on Earth. It wasn't confined by geography. It followed warmth and abundance wherever they existed. The global ocean was its territory, a single connected world long before humans conceived of borders. Its young were born live, as with other large sharks, and likely grew quickly to avoid predation. Nursery areas identified from fossil beds show concentrations of smaller teeth in shallow coastal regions, places where food was plentiful and large predators scarce. These nursery grounds were the foundation of its survival strategy, sanctuaries for the next generation. When those sanctuaries vanished during climate change, the chain broke. Evolution depends on stability at the base, and even the largest hunters rely on fragile beginnings. There are stories, of course, sightings, rumours, misinterpretations, of enormous shadows seen in deep water, of teeth pulled from strange contexts, of sonar traces that defy explanation. But the fossil record is clear. Megalodon's time ended millions of years ago. What remains is legacy, not presence. The deep sea is still vast enough to hide mysteries, but it doesn't hide giants of that kind anymore. Their absence is part of the ocean's equilibrium. What's left behind is influence, the idea of the giant predator embedded in the structure of marine life. Every shark carries a fraction of that blueprint. The ocean remembers the balance between hunter and prey, between abundance and collapse. The Megalodon was not just an animal. It was an era condensed into form, a moving threshold of what life could achieve in water. The teeth of Megalodon, scattered across the world, form a kind of fossilised map. They've been found in North America, Europe, Africa, Australia and Japan in layers of sediment that mark ancient coastlines. Each site tells a piece of the same story: warm seas, thriving food webs, and predators so large they reshaped entire ecosystems. To hold one of those teeth is to feel time reduced to weight. Its serrations, still sharp, remind us that power leaves tangible traces even when flesh and motion are gone. In the grand timeline of evolution, the age of Megalodon was brief, a few million years, a blink compared to the coral's patience or the trilobite's reign. But during that blink, the ocean reached one of its extremes. It tested how large a predator could grow, how far a design could stretch before the world itself changed around it. That experiment ended, as all extremes do, when equilibrium demanded correction. Even after its fall, the ocean's rhythm continued. New predators took shape, smaller but no less effective. The great whales evolved songs and migrations. The sharks refined their senses. The dolphins invented cooperation. Megalodon became a memory written into DNA, an absence that defined what followed. And in the spaces it once ruled, other ancient forces endured. Some were invisible, too small to cast shadows or leave teeth behind. They never chased, never struck, never needed to move fast. Yet they ruled in a different way, by numbers, by chemistry, by persistence. Long before the giants, they were already shaping the world, and long after they would still be here. The microbial masters of the sea, the unseen architects of life, continued their quiet dominion beneath it all. Long after the giants sank into the sediment of time, the ocean remained full of life, but its real power shifted somewhere else. The dominion of size had passed, and in its place came something quieter and far more permanent. The strength of the sea no longer depended on teeth or muscle or speed. It depended on the invisible. The smallest creatures, too small to see and too ancient to count, continued the work that had begun before any fish or coral or predator had existed. The microbial world, vast beyond comprehension, became the ocean's true empire. These were not rulers in the sense of command or conquest, but in persistence. They do not rise and fall like predators or kingdoms, they simply remain. Every drop of seawater, every cubic centimetre of sediment, holds more living cells than the human body holds in total. A single litre can contain 1 billion bacteria and tens of millions of viruses. Together they form the base of all marine life, the origin, the recycler, the unseen system that turns death into renewal. Their numbers dwarf everything else combined. They've existed for nearly 4 billion years, long before oxygen filled the atmosphere, long before the continent formed, and long before anything moved with intention. The ocean is not merely their home, it is their creation. To the naked eye, the sea looks empty beyond the shimmer of fish or the slow roll of waves, but under a microscope it's dense with motion. Chains of cyanobacteria drift like threads of green light, converting sunlight into energy and releasing oxygen as waste. Other bacteria float nearby, breaking down organic matter, digesting molecules too small for larger life to notice. Viruses outnumber them all, each a particle of genetic material wrapped in protein, endlessly infecting, replicating and transferring genes between species. This exchange, microscopic and constant, drives evolution in ways even the largest events in Earth's history cannot match. The giants were visible symbols of power, but the microbes are the substance of life itself. Long before multicellular organisms appeared, the ancestors of these microbes shaped the planet. Cyanobacteria were the first to perform oxygenic photosynthesis, splitting water to extract hydrogen and releasing oxygen as a byproduct. Over hundreds of millions of years, that waste gas transformed the atmosphere, oxidizing iron, forming new minerals, and creating the conditions for complex life. Without those bacteria, there would have been no ozone layer, no breathable air, no energy-rich environment for evolution to explore. The first global engineers were single-celled and blind, driven only by chemistry. The same processes continue now, unnoticed beneath the waves. Phytoplankton, the microscopic algae and bacteria that photosynthesize, produce at least half of the oxygen on Earth each day. Every breath humans take owes a debt to these drifting cells. They absorb carbon dioxide, convert it into organic matter, and sink slowly when they die, carrying carbon to the seafloor where it's trapped for millennia. This biological pump regulates the planet's climate. The ocean's carbon cycle isn't run by currents or storms, but by microbes performing endless silent work. Most marine microbes live not in isolation but in networks. Some form biofilms, thin layers on rocks, shells, or the skin of animals, where thousands of species interact. Others inhabit the guts of fish, the tissues of sponges, the mucus of corals. They recycle waste, fix nitrogen, and produce compounds that protect their host from disease. The coral's survival depends as much on its microscopic tenants as on its visible polyps. The balance of the reef begins at the scale of cells. Even in the darkest trenches where pressure could crush metal, microbes thrive. They live on heat and minerals released from vents using sulfur, methane, or iron instead of sunlight for energy. These chemolithotrophs, literally rock eaters, represent another form of life's ingenuity. They prove that biology doesn't need warmth or light or air to flourish. At hydrothermal vents, entire ecosystems depend on them. Giant tube worms, clams, and crabs feed on or host these bacteria in symbiosis. The energy that fuels them comes from the Earth's core, not the sun. These microbial communities were likely among the first ecosystems on Earth, and in some ways they've never changed. Their endurance across extremes is unmatched. Some marine microbes survive in ice, some in boiling vents, others inside rocks beneath the seafloor. There are bacteria trapped in ancient salt crystals that can be revived after hundreds of thousands of years. There are viruses that persist as genetic ghosts, integrating into the DNA of their hosts and waiting silently for the right conditions to awaken. They exist at every temperature, every depth, every chemistry the ocean offers. Life's adaptability begins and ends with them. The viruses, often considered non-living, play a paradoxical role in this system. They destroy and create simultaneously. Each day, marine viruses kill roughly 20% of all oceanic bacteria, releasing nutrients back into circulation. Without them, the system would stagnate, locked in imbalance. By breaking down cells, they feed the food web from the bottom up. At the same time, they transfer genes, moving useful traits, like resistance to toxins or the ability to metabolize new compounds, between species. Evolution in the ocean isn't only descent, it's exchange. The viruses are the couriers. At a molecular level, this constant traffic defines the ocean's memory. Genes that evolved billions of years ago remain in circulation, pass through uncountable generations. The enzyme systems that fix carbon, process nitrogen, or build cell walls are ancient, nearly unchanged since the dawn of life. The continuity is staggering. Every living thing in the ocean, from whale to microbe, uses the same basic chemistry, the same language of nucleotides and amino acids. The microbes wrote the code, and everything else reads it. Their importance goes beyond survival. Many marine bacteria and fungi produce compounds that influence global systems. Dimethyl sulfide, a gas released by certain plankton, contributes to cloud formation, affecting weather patterns. Other microbes produce antibiotics, toxins, or signaling molecules that shape interactions between species. The ocean's atmosphere, chemistry, and even climate owe their dynamics to the metabolic byproducts of invisible organisms. When viewed this way, the sea isn't just a body of water, it's a metabolic engine powered by uncountable reactions happening every second. Microbial mats, dense carpets of bacteria layered by colour and metabolism, are found in coastal shallows and tidal flats. They resemble living fossils, modern versions of the stromatolites that dominated ancient seas billions of years ago. Each layer performs a different task. Photosynthesis on top, sulfur cycling below, fermentation deeper still. These mats create self-sustaining systems that can persist for centuries. Some of the oldest living structures on Earth, still growing in Western Australia, are microbial reefs like these, barely changed since before animals existed. Standing above them, you can watch bubbles of oxygen rising through the water, the same process that made the world habitable continuing without interruption. The diversity among marine microbes is impossible to quantify fully. Genetic studies reveal new species every time researchers sample seawater from a new region. Entire phyla exist that no one has ever cultured in a lab, known only from fragments of DNA drifting in the water. The microbial world doesn't fit into the categories we use for larger life. Its boundaries blur constantly as genes move and species merge or divide. In that sense, evolution among microbes isn't a tree but a web, a dynamic network of exchange. The microbial ocean also acts as an archive. Chemical traces left by ancient microbes are preserved in rocks and sediments, marking shifts in climate and chemistry over geological time. Scientists analyze isotopes of carbon, nitrogen, and sulfur to reconstruct how microbial metabolisms shaped the planet's history. Every major environmental transition, the rise of oxygen, the cooling of the atmosphere, the expansion of ice, bears their fingerprints. They are both cause and record. In the present, human activity increasingly affects them. Rising temperatures, acidification, and pollution alter the delicate chemistry that defines microbial balance. Some species bloom excessively, creating oxygen-depleted zones that suffocate larger life. Others vanish, taking with them the functions they performed, yet the system remains resilient. Microbes have survived asteroid impacts, volcanic winters, and ice ages. They adapt not by resistance but by replacement. When one species fails, another evolves or migrates into its niche. Extinction, for them, is a local event, never a global one. If one could shrink to their scale, the ocean would look entirely different. Surfaces would be vast landscapes of chemical gradients, where energy flows like wind and nutrients drift like dust. A single particle of organic matter becomes an island colonized by bacteria, grazed by protozoa, and dissolved by enzymes. The physics that dominate our world, gravity, inertia, matter less than diffusion, reaction, and randomness. Yet even here patterns emerge. The same rules of balance and feedback govern everything from the scale of microbes to that of whales. Life at every size obeys the same logic. Perhaps what's most remarkable is that, despite their invisibility, these tiny tyrants control everything else indirectly. They set the limits of productivity, the pace of decay, the flow of nutrients. When they thrive, the ocean supports abundance. When they falter, ecosystems collapse. They are both foundation and governor, the unseen majority that ensures stability through constant change. Their rule is quiet, distributed, and absolute. In the open ocean, where currents run deep and slow, most of what sinks eventually returns to them. The carcass of a whale becomes a microbial city as it falls, first stripped by scavengers, then dissolved by bacteria until only minerals remain. Every death, no matter how large, ends as microbial activity, breakdown, recycling, reintegration. The microbes are the ocean's final arbiters. There's a strange humility in that realization. The creatures that build shells, swim with fins, or sing with lungs all depend on the chemical economy of entities without faces or form. The cycle of creation and decay belongs to them. They don't dominate by will, they dominate by presence. In every ocean, at every depth, in every condition, they are there, unchanged and indispensable. Even their simplicity hides sophistication. Some bacteria communicate through chemical signals, coordinating behavior across millions of cells, a phenomenon known as quorum sensing. When their numbers reach a threshold, they act collectively, producing light, releasing toxins, or forming biofilms. The glowing waves of bioluminescence seen at night on tropical shores are the visible expression of that collective behavior. Each spark of light is a microbial voice responding to density, transforming chemistry into communication. The beauty of it is functional, but no less extraordinary for being so. In that glowing water, one can glimpse the ancient truth of the sea, that life's most powerful forces are almost always invisible. The microbes don't compete for our attention, and they don't need recognition. Their rule isn't theatrical, it's constant. Everything else, from the coral to the shark to the whale, depends on them in ways that remain mostly unseen. And while the giants of the past turned the sea red with motion, the microbes turn it alive through stillness. Their quiet cycles keep the planet breathing. Their metabolism is the rhythm of continuity. The giants had their age and the armoured had theirs, but these tiny forms never surrendered theirs. Their empire stretches backward to the beginning and forward beyond any foreseeable end. Even now, as the ocean changes under the influence of heat and human disruption, they adjust. They find new chemistry, new pathways, new alliances. The microbial realm is too vast to fail, too adaptable to end. It represents life's truest form, persistence without arrogance, dominion without violence. Above them, the visible ocean continues its dance. The predators, the reefs, the drift of plankton. But beneath that motion, the foundation hums. The microbes work, unseen, uncelebrated, and eternal. And in the glow of their living light, the next layer of the ocean begins to stir. Creatures that have turned light itself into a weapon. Not giants of flesh, not architects of stone, but hunters who rule the twilight with chemistry and precision. The bioluminescent predators rise, their bodies flickering like stars trapped underwater, each pulse an ancient language of survival. The water darkens into a zone where sunlight weakens and colour dissolves. The upper ocean's brightness thins to a dim blue haze, and then to grey. Here begins the realm scientists call the mesopelagic, the twilight zone. It stretches from roughly 200 metres to 1,000 below the surface, where day is reduced to memory and night is not yet complete. In this world of partial light, visibility becomes a matter of survival, and light itself becomes a tool. The creatures that live here have turned biochemistry into strategy. They are predators and prey that use light, the way land animals use sound or colour, an evolutionary conversation that has continued for millions of years. The Twilight Zone is the most populated region of the ocean, though almost no one ever sees it. Billions of fish, crustaceans and gelatinous creatures drift through it, forming the largest migration on Earth. Every night they rise toward the surface to feed, and each morning they descend again, following the slow shift of illumination. It's a movement so vast it affects global carbon cycles, moving organic material between depths daily. Within that migration, certain creatures carry their own lanterns, organs that generate light through chemistry. These are the bioluminescent hunters, the predators of light, adapted to live in darkness by mastering its illusion. Bioluminescence is not rare in the ocean. It's nearly universal at depth. About 90% of animals below 1,000 metres can produce light. The mechanism is simple in principle but endlessly variable. Specialised cells called photocytes or structures called photophores contain luciferin, a light-emitting molecule, and luciferase, the enzyme that triggers its oxidation. The reaction releases photons instead of heat. Cold light, efficient and silent. Different species control the colour and pattern through chemistry and tissue filters. Blue-green wavelengths dominate because they travel farthest underwater. Red light fades first, which is why some deep species evolved to produce or perceive red as a form of invisibility. The first creatures to wield light likely did so defensively. A sudden flash can startle predators, drawing attention away from a fleeing body. Some release clouds of glowing mucus, confusing attackers. Others drop luminous particles, leaving behind decoys. Over evolutionary time, these defensive sparks became signals, then lures, then weapons. What began as avoidance turned into manipulation. The predators of light use bioluminescence not just to hide, but to deceive. Perhaps the most famous is the anglerfish. Its body is compact, its mouth filled with sharp teeth that angle inward to prevent escape, and from its head extends a modified fin ray tipped with a bioluminescent lure. The light comes from symbiotic bacteria living inside the lure's flesh, fed by the fish's blood and regulated by nerves. The anglerfish dangles this glowing bait in front of its mouth, moving it gently like a drifting organism. Smaller fish, drawn by the light in the darkness, swim closer to investigate, and the mouth closes around them in a fraction of a second. It's a perfect trap. Motionless, energy efficient, and nearly invisible until it's too late. There are hundreds of anglerfish species, each with variations of the same theme. Some live near the surface, others in abyssal depths. Some produce steady light, others pulse or flicker. The pattern of the glow may even help individuals recognize their own kind. In species that live thousands of meters down, males are tiny compared to females, and reproduction takes an unusual form. When a male finds a female, he bites her and fuses permanently, his body dissolving until only his testes remain attached. The pair become a single organism, sharing blood and chemistry. In the deep sea, where encounters are rare, this merging ensures continuity. Even reproduction bends to the logic of scarcity. Not all bioluminescent hunters rely on stillness. Some use light for active camouflage in the opposite direction. Counter-illumination is a strategy where an animal matches the faint light coming from above, rendering itself invisible from below. Lanternfish, hatchetfish, and squid possess arrays of photophores on their undersides, adjusting brightness in real time based on ambient light. Sensors in their skin detect the surrounding illumination and fine-tune the glow to match. When seen from beneath, they blend seamlessly with the dim surface above. It's the ocean's version of adaptive camouflage, performed not with pigment but with living light. Lanternfish are small, but they shape the planet. They are the most abundant vertebrates in the world, numbering in the quadrillions. Their daily migration, rising at night to feed and sinking by day, moves more biomass than all human fisheries combined. They feed on plankton, which in turn feeds larger predators. Their bioluminescence helps them navigate, communicate, and hide within that migration. They are both prey and participant in an endless exchange of energy. Some predators use light offensively, like searchlights. The dragonfish, a slender predator of the twilight, carries photophores along its body and beneath its eyes. Uniquely, it can produce red light, which most deep-sea animals cannot see. This gives it an advantage. It can illuminate prey without revealing itself. Its mouth is filled with long, transparent teeth that reflect almost no light, making them invisible. When it opens its jaws, it becomes a trap of glass and shadow. The red beam falls on unsuspecting prey, and the strike follows before the target even realizes it's been seen. Other dragonfish species add blue or green bioluminescence for signaling, creating flashes along their sides like coded language. These patterns may help them identify mates or warn rivals. The complexity suggests not just reaction, but communication, a dark water language made of light. The ability to produce multiple colours is rare, but where it appears, it opens new evolutionary possibilities. Light becomes information, and in the abyss, information is survival. Squids, the old masters of adaptation, also dominate here. Some species, like the firefly squid of Japan, migrate to shallower waters in spring, their blue photophores turning coastal seas into constellations. Others, like the vampire squid, inhabit the deep oxygen minimum zones, where few others can live. Despite its name, the vampire squid doesn't hunt aggressively. It floats, extending filament-like appendages to collect drifting organic debris. When threatened, it turns itself inside out, wrapping its webbed arms over its body and flashing light from the tips. This sudden burst startles predators long enough for escape. Even passivity in the deep carries brilliance. In colder waters, certain krill species emit light in rhythmic pulses, creating waves of bioluminescence that ripple through the water as they swim in swarms. These displays are not random. They help maintain group cohesion and may confuse predators. The result, from a distance, looks like sheets of living light moving through the darkness, an oceanic aurora generated by countless tiny bodies. The mechanics of bioluminescence are ancient and have evolved independently many times. Different species use different luciferins and enzymes, suggesting that nature discovered the trick repeatedly under similar pressures. Where sunlight disappears, the incentive to make your own becomes universal. In that sense, light in the deep ocean is not decoration but adaptation. It's the currency of survival, traded in flashes and glows that span millions of years of refinement. Even among bacteria, bioluminescence has meaning. Some free-living species glow continuously, while others emit light only when densely packed. This collective glow may attract fish, which ingest and transport them to new habitats. Inside fish, guts, or decomposing carcasses, they flourish, continuing the endless cycle of dispersal. In shallow tropical waters, when waves break at night, the sparkle that trails from your hand or a boat's hull comes from such bacteria. light emitted by single-celled organisms as a byproduct of metabolism, millions of years old and still efficient. The evolutionary cost of light production is small compared to its benefit. In complete darkness, a faint signal can mean the difference between mating or isolation, predation or escape. The chemical reaction consumes energy, but the payoff is existence. Some scientists propose that bioluminescence may have first evolved as a way to neutralize excess oxygen within cells, a metabolic byproduct turned into communication. If true, the first lights of the ocean weren't meant for others to see at all. They were accidents of chemistry that later became tools of survival. In modern research, bioluminescent systems have become keys to understanding biology itself. The green fluorescent protein, discovered in a jellyfish, now illuminates living cells in laboratories worldwide, revealing processes invisible to human eyes. The same chemistry that helps a fish hide in the abyss helps scientists see the inner life of neurons and genes. The deep sea, once thought isolated, has become a mirror for our own search for understanding. To stand on a ship at night and look over the side is to see traces of this world. The water glows faintly where the hull disturbs it, each droplet a brief point of light. In tropical seas, swimmers leave trails that shimmer and fade like liquid constellations. It feels magical, but it's entirely real, the product of chemical reactions happening in trillions of cells, each one responding to motion and chemistry. The light is ancient, but it's never old. For the creatures that live entirely in the twilight and below, this luminosity defines identity. Some species are visible only through the light they make. Their bodies are transparent or black, absorbing nearly all reflection. The only way to detect them is by their glow. In a sense, light is their body language, their camouflage, and their weapon all at once. In a world without external illumination, every organism becomes its own star. There's an order to this nocturnal world. The surface layers fade, the twilight brightens with motion, and below that lies complete blackness, the abyssal zone. In that lowest region, bioluminescence becomes rarer but more dramatic. Creatures there emit light not for communication or hunting, but as part of the final adaptations to eternal night. Some flash only when disturbed, like alarms. Others keep a steady glow, using it to lure prey in a world where energy is scarce. Each pulse is costly, each spark deliberate. Bioluminescence connects every layer of the ocean's depth. From plankton at the surface to predators miles below, the same phenomenon links all scales of life. The distribution of light marks transitions in ecosystem structure, temperature and chemistry. To scientists mapping these patterns, bioluminescence is both biological and planetary, a visible signature of how life persists in places beyond sunlight. For the bioluminescent hunters themselves, the system is simple. Darkness is opportunity, light is control. The anglerfish waits, the dragonfish prowls, the squid confuses, the krill gathers. Every act of glowing is a negotiation with the surrounding void. They rule through illusion, through the careful use of what little visibility exists. Their hierarchy is defined not by strength or size, but by timing. Whoever controls the moment when light appears or disappears wins. And above them all, the faintest rays from the surface still fall, filtered through kilometers of water. To a dragonfish, those rays mean the start of retreat. To a lanternfish, they signal ascent. The daily migration begins again, an endless tide of glowing bodies moving in synchronization with the planet's rotation. The deep breathes light in and out every 24 hours, a pulse that has continued for as long as these creatures have existed. In the transition between night and day, when the surface warms and the twilight fades, the bioluminescent hunters sink again into obscurity. Their light fades with them, absorbed by the dark. But even as they vanish, they leave traces, glowing particles, drifting bacteria, faint halos where chemical reactions linger. The ocean's blackness is never complete. It always carries the residue of light. Far below, in the regions where even bioluminescence grows rare, another form of endurance takes over, not through sight, but through time itself. The slowest creatures, built for millennia rather than moments, inhabit that depth. They are the ones that measure survival in centuries, the living record of evolution's patience. While the predators of light flicker briefly and vanish, these others remain still and enduring, marking the ocean's rhythm with their longevity. Evolution has many tempos, and in the abyss, the next begins with time measured not in flashes but in eras. Below the flicker of bioluminescence, below the zones where light still carries meaning, the ocean changes character. Motion slows, chemistry stabilizes, and the concept of time begins to stretch. Down here, beneath 3, 4, even 10 kilometers of water, evolution measures itself differently. The ocean's clock doesn't tick like ours. It moves in tides, in chemical gradients, in slow exchanges between the living and the mineral. Every organism, every reaction, exists within a rhythm that makes centuries feel brief and extinction feel like a pause. The deep sea doesn't forget, it adjusts. The idea of time underwater is not about minutes or days, but processes. The slow drift of sediment, the accumulation of shells, the quiet formation of mineral nodules around particles of dust. In the upper layers, life happens fast. Plankton bloom, fish hatch, predators hunt. But as pressure builds and light disappears, motion becomes expensive, and the only way to survive is to slow down. The creatures that live in these depths stretch their metabolisms until each heartbeat, each reproduction, each cell division takes the smallest possible toll. Their pace isn't laziness, it's precision. Some of the longest-lived animals on Earth live here, or depend on these deep processes. The Greenland shark, cruising in near-freezing waters, grows only a few centimeters each year. Radiocarbon dating of its eye tissue revealed individuals over 4 centuries old, perhaps more. These sharks were alive before industrial civilization, before telescopes mapped the stars, before the light bulb imitated the very glow that the deep sea mastered first. They drift through the darkness not as relics but as proof that life can endure almost indefinitely when it spends energy carefully. Their tissues metabolize slowly, their growth almost imperceptible, their movement minimal. For them, time is less an arrow than a current that can be resisted. In the same cold depths, clams and corals also live for centuries. Deep water corals, such as the black corals and precious red corals, form branching skeletons on seamounts thousands of meters below the surface. Each layer of calcium carbonate records changes in the surrounding water, shifts in temperature, carbon and nutrients, like rings in a tree trunk. Some coral colonies date back 5,000 years. They have outlived civilizations, recorded volcanic eruptions, and silently archived chemical evidence of every industrial shift humans have made above them. Their growth rates are measured in millimeters per decade. To exist that slowly is to turn life into geology. Time, in the ocean, has always been cyclical. Currents rise and fall, ice ages advance and retreat, salinity and temperature fluctuate, and species appear, change, and vanish. The organisms that endure longest are those that align themselves with these cycles instead of resisting them. Evolution in the sea doesn't always mean improvement or complexity. It often means calibration, small genetic adjustments that keep a species synchronized with its surroundings. The ocean selects not only for form but for tempo. At the microbial level, this synchronization becomes absolute. Deep-sea bacteria living in sediments experience environments so stable that their replication rates are measured in centuries. Studies of DNA in core samples show lineages that have changed almost nothing in millions of years. They persist in a near-suspended state, feeding on the faint chemical traces of decaying matter that sinks from above. The energy they consume in a year would barely power a single human cell for a few seconds, yet over time, they alter the chemistry of entire ocean basins. life at the bottom of the sea has discovered that the slower it moves, the longer it lasts. Even the geological processes of the ocean mimic this rhythm. The seafloor spreads as magma rises from ridges, cools, and drifts outward over tens of millions of years. As crust sinks back into trenches, it carries organic carbon and microbial life with it, subducting them into Earth's mantle. Some of that carbon eventually returns through volcanic outgassing, completing a cycle that may take hundreds of millions of years. The ocean's clock, then, isn't just biological, it's planetary. Every organism that dies and sinks contributes to the slow ticking of that clock. Every shell that settles on the seafloor a unit of time in geological notation. For the life that inhabits these depths, adaptation means aligning physiology with those immense cycles. Some deep-sea fish produce antifreeze proteins to remain active near freezing temperatures. Others evolve translucent tissues to reduce metabolic cost. Reproduction happens rarely and deliberately. Larvae drift in currents for months before settling. The stability of their environment means that fast evolution isn't necessary. Mutations accumulate slowly, selection acts subtly, and diversity is maintained through endurance rather than turnover. The ocean's clock also runs through vertical motion. Each night, billions of organisms rise toward the surface to feed and descend again by day, a migration older than any continent. It's the ocean's heartbeat, regulating carbon flow and oxygen distribution. This daily cycle compresses evolutionary time into ritual. Species that participate in it evolve traits linked to synchronization, light sensitivity, buoyancy control, and metabolic cycles that anticipate dawn and dusk even in the absence of visible light. In that way, the rhythm of the planet's rotation is imprinted on the biology of every creature that drifts in water. In the shallows, time feels faster. Coral reefs rebuild within centuries. Fish populations recover or collapse within decades. Plankton blooms last days. But in the deep, where pressure reaches hundreds of atmospheres, where the sun never penetrates, the boundaries between life and death blur. A carcass that falls from above becomes an ecosystem that can last for decades. A whale fall, as scientists call it. Bacteria, worms, and crustaceans colonize the remains, feeding entire communities until even the bones dissolve into sediment. Each whale fall marks a brief pulse in the slow metabolism of the abyss, another second on the ocean's clock. Evolution's measurement of survival is not linear in this world. It's adaptive equilibrium, change held in balance with stability. A lineage that evolves too quickly risks losing its fit with an environment that doesn't change often. One that evolves too slowly may fail when rare shifts occur. The balance defines longevity. The kilacanth, the nautilus, the deep-sea corals and the sharks of the polar night all represent lineages that found their equilibrium and kept it for eons. Their continued presence tells us that progress in evolution isn't a race forward, but a search for rhythm. At a molecular level, the same principle applies. DNA repair mechanisms, protein stability, and metabolic control all slow in deep-sea organisms. Some possess unique enzymes that operate efficiently under extreme pressure, but become unstable near the surface. Others adjust their cell membranes to remain flexible despite the crushing weight above. These adaptations don't just allow survival, they define a different pace of living, where energy is currency and movement is debt. Even the concept of aging shifts underwater. Some organisms, like certain jellyfish, appear to escape senescence entirely. When stressed or injured, they revert their cells to an earlier stage, essentially starting life again. Turritopsis dorni, often called the immortal jellyfish, can cycle between maturity and youth indefinitely, provided conditions remain stable. It's a biological loop, time folded inward. Such organisms don't experience life as a straight line from birth to death, but as recurrence, a small reflection of the ocean's own recursive patterns. In other species, longevity arises not from reversal, but from efficiency. Bivalves like the ocean quahog live for more than 500 years, their metabolic rate so slow that change becomes barely measurable. Their shells accumulate layers like pages in a book, each recording temperature and chemistry through isotopic ratios. When scientists study them, they read climate history written in calcium and protein, one thin line per year. A single clam can tell the story of centuries of storms and calm. From an evolutionary standpoint, the ocean's clock also dictates the emergence and extinction of species. The fossil record preserved in marine sediments shows cycles of diversification followed by stasis. After major disturbances, volcanic events, asteroid impacts, glaciations, life rebounds quickly near the surface but slowly at depth. The deeper ecosystems absorb change like sponges, their inhabitants altering behaviours and chemistries rather than forms. This buffering effect gives the deep sea its timelessness. It's both graveyard and nursery, a place where extinction's impact softens and where the next waves of adaptation begin. If we could compress all of oceanic evolution into a single day, the microbes would appear at dawn, the trilobites by mid-morning, the fish around noon, the sharks and corals by early afternoon, the whales near evening, and humans only seconds before midnight. Through it all, the ocean's chemical balance, its rhythms of temperature and salinity, would serve as the constant metronome. What we think of as sudden evolutionary leaps are, in the ocean scale, just quick variations in a very slow song. Even now, the ocean continues to measure time through invisible processes: the slow uptake of carbon dioxide, the burial of organic matter, the drifting of planktonic shells that will one day become chalk and limestone. The cliffs and mountains on land are ancient coral reefs and plankton beds transformed into stone, the solid remnants of what once floated freely in water. The planet's geological clock and its biological one are synchronized through the ocean. Human influence, though immense in surface time, barely registers yet in deep time. Plastic debris, chemical runoff, and warming currents are new entries in the ocean's record, thin layers forming across the seafloor that future strata will mark as a boundary, a signal of sudden change. To the ocean's clock, it's a rapid tick, an instant disruption in an otherwise steady pulse. Whether that disruption lasts depends on how the systems of chemistry and life readjust. They always have before, but the cost of each reset has been mass extinction. The clock doesn't stop, but it resets itself by erasing what can't adapt. Studying the deep ocean gives a perspective on time that challenges every human assumption. Our civilization measures progress in decades and centuries. The sea measures it in ages. A coral colony's lifespan spans dynasties. A microbial mat records conditions from before language. The deep currents take 1,000 years to complete a single circuit from pole to pole. Even light, which travels instantly to our eyes, takes minutes to fade completely through the densest water. Everything down here has learned patience beyond our imagination. For life in the ocean, time is not an enemy or a countdown, but an element to inhabit. Species rise and fall within it the way waves rise and fall on the surface. What remains constant is the rhythm, the repetition of pattern that sustains complexity. The ocean doesn't preserve everything, it preserves the conditions for continuation. Evolution's measurement of survival in this context is endurance through equilibrium. To exist long enough to maintain balance is success. To overreach, even briefly, is failure. In that sense, the ocean itself is a clock wound by the planet's heat and tides, keeping the measure of stability across billions of years. Every organism, from the smallest bacterium to the longest living shark, moves in time with it. We measure seconds and years, but the ocean measures persistence. And far above, where the water meets air and motion returns to the scale we recognize, time regains its speed. The tides wash over coasts shaped by millennia, eroding, rebuilding, erasing. The same patterns of survival that govern the deep echo at the surface, where creatures live faster but follow the same cycles of adaptation and endurance. The ocean's clock reaches everywhere, its rhythm set not by any creature but by the total sum of them all. And within that rhythm, some species have discovered another form of endurance, not through slowness or longevity, but through stillness, learning to survive by doing almost nothing, by matching their heartbeat to the environment so precisely that they become indistinguishable from it. In the next layer of this great continuity, survival itself takes on a new meaning. To remain by being still enough that change passes around you like current around stone. There is a point in the ocean where motion ceases to be the measure of life. The great migrations end, the hunters that flash and dart are gone, and what remains are creatures that seem to have chosen silence as their defence. In this world, to move is to risk, to expend is to vanish. Energy is precious, and the best survivors are those that have learned to wait. The ocean, vast and indifferent, favours efficiency over spectacle. It rewards the creatures that waste nothing, those that have built their entire existence around restraint. Survival, at its most refined, has nothing to do with aggression. It is the art of stillness. The deep sea, the slow currents of the abyss, and the quiet shallows beneath reefs all share this truth. In every habitat there are animals that survive by blending into the background, by conserving energy, by trusting patience over power. They are not weak, they are perfected. The ocean is full of ambush predators that rely on invisibility, parasites that outlast their hosts, and symbionts that live on cooperation rather than conquest. When energy is scarce and competition endless, stillness becomes not a pause but a strategy. Take the frogfish. It lives among sponges and corals, shaped almost exactly like the rocks and algae around it. It does not swim in search of prey. Instead, it anchors itself, moving only when necessary. On its head, a small lure, a fleshy filament tipped with a mimic of a worm or shrimp, dangles just above its mouth. The frogfish twitches it slowly, a patient performance in a theatre of predators. When a smaller fish approaches, attracted by the lure's motion, the frogfish opens its mouth in a fraction of a second, drawing in water and prey faster than the blink of a human eye. It consumes and returns to stillness, its camouflage undisturbed. Hours may pass before it moves again. Its body language is silence, its power is patience. The same principle defines countless others. The stonefish, venomous and motionless, spends most of its life buried in sand or coral rubble. Its dorsal spines carry one of the most potent toxins known among fish, but it doesn't use it for offence. It waits, perfectly disguised, until something edible wanders close. Its venom is protection, not aggression, a deterrent against careless curiosity. The stonefish is almost invisible, a living sculpture shaped by the currents themselves. Octopuses, though capable of astonishing motion, are also masters of stillness. The mimic octopus and the larger reef-dwelling species often freeze completely, their skin shifting colour and texture to match surroundings. Their chromatophores, iridophores, and papillae work in layers, changing pigmentation and reflection within milliseconds. They can imitate coral, sand, even other animals, not through movement, but through total immersion in environment. The moment an octopus stops moving, it doesn't just hide, it vanishes from perception. Its intelligence lies not only in problem solving, but in the ability to become invisible by choice. Stillness isn't limited to predators. Many prey species survive through the same mechanism. Flatfish, when young, start life swimming upright like any other fish. As they mature, one eye migrates to the other side of the head, and their body flattens. They spend adulthood lying against the seabed, blending with sand. When disturbed, they bury themselves completely, leaving only eyes exposed. A single twitch of fin or flick of sand betrays them, so they learn to remain motionless until danger passes. Evolution favoured not speed, but invisibility. The art of doing less extends to entire ecosystems. Coral reefs, for all their motion and colour, depend on organisms that hardly move at all. The corals themselves are colonies of polyps that spend their entire lives fixed to rock. Their partnership with photosynthetic algae provides energy without hunting. The polyps extend small tentacles to capture passing particles, but their main sustenance comes from light harvested by their symbionts. The reef's vast construction, stretching for kilometres, is built by creatures that never travel more than a few centimetres. Their stillness becomes architecture, turning energy from the sun into stone. Sea anemones and sponges share this philosophy. They filter water, extracting microscopic food as currents pass through them. They do not chase, they receive. The sponge, one of the oldest animal lineages, is built from channels and chambers designed for flow. Each cell has a job. Some generate movement of water, others capture nutrients. The organism as a whole remains fixed, drawing life through itself continuously. It has no nervous system, no aggression, no hierarchy. Its structure embodies the ocean's equilibrium, motion passing through stillness. Even in the open sea where drifting seems chaotic, stillness has form. Jellyfish pulse gently, but spend most of their time carried by currents, conserving energy through surrender. They move by being moved, letting the water's rhythm dictate their path. Their bodies, composed mostly of water themselves, have little weight and little will. They are the definition of evolutionary minimalism. No bones, no brain, no defences beyond transparency and toxin. Yet they have outlived almost every other lineage. Their secret is that they demand almost nothing. On the microscopic scale, planktonic organisms do the same. Many can swim, but most drift, relying on shape rather than effort. Some form delicate chains or spikes that increase surface area and slow sinking, allowing them to remain suspended longer in sunlight. They let the ocean carry them, their existence tied to its movement. In the vast engine of marine ecology, they form the base of the food web without ever needing to pursue or flee. Their stillness sustains everything above. The logic of stillness extends even to behaviour and interaction. Many species form symbiotic relationships that reduce the need for aggression. Cleaner fish feed on parasites from larger fish, who tolerate their presence rather than consume them. The relationship saves energy for both. Sea cucumbers recycle detritus, digesting organic matter from sand and returning nutrients to the ecosystem. Their method is patient, continuous, and crucial. The ocean's balance depends on these understated participants that survive by quiet cooperation. Aggression, where it exists, often carries cost. Predators expend energy, risk injury, and depend on abundance to sustain hunting. In contrast, species that rely on patience can endure scarcity. During lean times, motionless feeders, scavengers, and filterers continue their cycles. They are the insurance policy of ecosystems, slow, steady, reliable. In evolutionary terms, aggression is a specialization. Stillness is resilience. There are extremes of this adaptation. Deep-sea holothurians, relatives of sea cucumbers, lie motionless for days, absorbing nutrients from sediment. Some species can slow their metabolism to near dormancy when food is scarce. They respond not with panic or migration, but with pause. Others, like the Antarctic icefish, live in water cold enough to freeze human blood. Their metabolism is so slow that movement is reduced to minimal fin flicks. They produce antifreeze proteins that prevent ice crystals from forming in their veins. These proteins cost energy, but far less than the heat or speed required by tropical species. In such places, stillness is survival's only option. When researchers explore the deepest trenches with submersibles, they often find animals that seem indifferent to the intrusion of light and machines. Giant amphipods, sea stars, and fish hover slowly, barely reacting. Their lives occur at a scale of time and energy where disturbance means little. They live close to geological pace, unhurried by the presence of anything that doesn't last. To observe them is to witness evolution stripped of aggression entirely. A calm persistence that endures every shift of climate, chemistry, and catastrophe. On a different scale, the ocean's microbial world mirrors this. Many bacteria enter dormant states when nutrients run low, forming spores that can survive for millennia. Some remain viable in sediments for millions of years, reawakening when conditions change. Their stillness is absolute, yet it is not death. It's suspended readiness. This strategy ensures that even when entire ecosystems vanish, the seeds of renewal remain embedded in the seabed, waiting for balance to return. There's a common thread through all these examples. Life in the ocean rarely fights for control. It adapts by yielding. Predators ambush rather than chase. Prey hide rather than flee. Ecosystems depend on cooperation rather than conquest. The ocean is too vast and too unpredictable for aggression to remain effective for long. Those who dominate briefly, like the megalodon or ancient reptiles, eventually disappear when conditions shift. Those who adapt through restraint persist across epochs. Stillness in this context is not passive, it's active alignment. It means sensing environment precisely enough to know when not to act. It's the discipline to conserve energy, to minimize exposure, to exist in harmony with surroundings. For an octopus blending into coral, for a sponge filtering in current, for a shark gliding slowly through deep water, stillness is the most complex form of awareness. It's a dialogue with physics and chemistry at every moment. In human terms, aggression seems powerful because it's visible, but in nature's long experiment, visibility often leads to vulnerability. The ocean's most successful inhabitants are those we rarely notice. They've mastered the art of existing without disruption. Even when they move, it's with such precision that motion appears calm. The manta ray, with its slow, graceful loops through plankton clouds, embodies this principle. It could move faster, but it doesn't need to. Each movement is efficient, each turn calculated. It lives as though aware that time and energy are linked currencies. Stillness also defines the rhythm of the tides, the steady pulse of planetary motion that underlies everything. The moon's pull raises and lowers billions of tons of water every day without aggression, without strain. That same force governs coral spawning, fish migration, and even the timing of microbial blooms. The ocean's greatest motion is itself a form of stillness, predictable, cyclical, balanced. Every organism that synchronizes with it gains stability. Those that resist it are washed away. When we imagine survival, we often picture struggle. But the ocean shows that endurance often means the opposite, reducing struggle until it disappears. The most stable ecosystems are those in equilibrium, where each species takes only what it needs, where stillness prevents collapse. Even predation fits into this. Regulated, efficient, rarely wasteful. There is no cruelty in it, only exchange. For billions of years, this principle has shaped evolution quietly. From the earliest microbial mats that lay immobile in shallow seas to the corals, the flatfish, the drifting jellyfish, and the patient predators of the abyss, stillness has written the ocean's longest story. It's not the absence of life, but its most refined expression, a response to the oldest challenge, how to survive when everything changes but the need to endure remains. And even now, as the ocean warms and acidifies, as human noise and industry reach its depths, this strategy continues to prove itself. Some species migrate to cooler waters, others shrink, reproduce faster, or form new symbioses, but many simply wait. Evolution, like the tide, favours patience. The ocean will shift, and in time, the ones that can remain still long enough will reclaim the spaces we disturbed. They always have. Above the slow rhythms of the deep, there's another form of survival beginning to unfold, not one of hiding or waiting, but of transformation. The ocean that once shaped the ancient and the still is now absorbing the byproducts of our brief, fast civilization. What survives next will be what can coexist with what we leave behind. Somewhere within that coming future, the silent endurance of stillness will meet the noise of human change, and out of that collision, the next chapter of survival will emerge. The ocean never forgets. Everything that touches it, everything that falls into it, everything that breaks within it becomes part of its slow memory. For billions of years it has recorded life through sediment and chemistry, through shells turned to stone, through skeletons pressed into shale. It holds the stories of creatures long gone and the traces of those still drifting above it. And now, for the first time, it holds pieces of us. The human era, brief and bright compared to the ancient span of evolution, has left a layer across the seafloor that will one day harden into record. A new stratum of the planet's archive, unmistakable and permanent. These are the future fossils. They are not made of bone or shell or coral, though some mimic those forms. They are made of what we have built and discarded. Fragments of plastic, metal, glass, rubber and chemical residue that have entered the sea through rivers, wind and rain. Over time, these materials sink, degrade or transform, settling among the biological debris that the ocean accumulates continuously. Each particle joins a sedimentary story billions of years in progress. The difference is that these new traces are alien to natural chemistry. They will not dissolve or erode in the same cycles that shaped the fossil beds of ammonites or trilobites. They will endure differently, chemically stable and indigestible, the physical imprint of our speed. When scientists collect core samples from the deep ocean today, they find layers that correspond to major global events, volcanic eruptions, meteor impacts, mass extinctions. In each, the composition of sediment changes abruptly. Now there is a new layer forming, filled with synthetic polymers, carbon soot and isotopes from nuclear testing. It begins in the mid-20th century and continues thickening with every passing year. Future geologists, if any remain, will see it as clearly as we see the boundary between the Cretaceous and Paleogene, the line that marks the end of the dinosaurs. Our layer will tell the story of the Anthropocene, the epoch in which the ocean became both witness and victim of human activity. Among the most enduring of these artifacts are microplastics. They are fragments smaller than a grain of sand, created when larger debris breaks apart or when fibres from clothing and packaging escape into waterways. They drift through every current, settle on every seafloor and mix into every layer of the marine food web. Plankton ingest them unknowingly, mistaking them for food. Fish eat the plankton. Larger predators eat the fish. Eventually the material travels up the chain until it returns to us. The cycle of consumption has become circular. The ocean is feeding back what we have given it. Yet even this contamination, unintentional and destructive as it is, becomes part of the geological narrative. Plastics, when buried and compressed over time, may form new rock-like composites, plastiglomerates, mixtures of molten plastic, sand and shell fragments that harden together. These materials, once formed, can last for millions of years, resistant to erosion and dissolution. They will become future fossils, the unmistakable markers of our industrial moment. They will not resemble anything that came before. To future eyes, human presence will appear as a thin artificial rainbow in the planet's sedimentary record. Beyond plastic, there are subtler imprints. Carbon dioxide absorbed from the atmosphere alters the pH of seawater, shifting the balance of dissolved minerals. The shells of plankton and corals grow thinner as calcium carbonate becomes harder to form. When these shells fall and accumulate, they will create strata distinct in composition, lighter, more fragile, chemically changed. Ocean acidification is not visible, but it leaves a chemical signature that will outlast every living generation. Even if all emissions cease tomorrow, the record would remain embedded in the carbonate skeletons of organisms yet unborn. The ocean also keeps traces of radiation. After mid-century nuclear testing, isotopes like cesium-137 and strontium-90 spread globally, settling into sediments and entering food webs. These isotopes decay predictably, forming a precise timestamp for this period of history. Long after buildings crumble and languages disappear, their decay curves will continue, telling time for us in the deep. The planet itself will remember the exact moment when we split the atom and scattered its byproducts through air and water. Metallic residues from mining, industry and technology also accumulate quietly. Aluminum, titanium, copper and rare earth elements, once buried deep underground, now appear in measurable quantities in marine deposits. They are joined by synthetic chemicals, from fertilizers to pharmaceuticals, molecules that no organism evolved to process. Many of them bind to organic material and sink, forming complex new sediments. Over geological time, these substances will mix, fuse and transform into minerals unlike any seen before. Each generation of our civilization adds its own chemistry to the recipe. There are other forms of legacy less visible but equally enduring. Sound travels through water faster than through air, and modern shipping, drilling and sonar have filled the ocean with constant low-frequency noise. Whales and fish that once navigated through silence now live within a steady industrial hum. This acoustic residue does not fossilize, but its biological effects will leave traces in bone structure and migration patterns recorded in the future's data. Silence, once the ocean's dominant condition, has become rare. Heat, too, is a legacy. The ocean absorbs more than 90% of the excess energy trapped by greenhouse gases. It warms slowly but inexorably, expanding and altering circulation. Currents that once defined climate patterns for millennia are shifting. The deep, once isolated from surface changes, is gradually feeling the difference. This thermal imprint will shape sedimentation rates, oxygen levels, and the distribution of species for millions of years. It will become another line in the archive, a thermochemical signal of our brief intensity. Despite this, the ocean remains resilient. Life reorganizes. Microbes evolve to digest plastics. Algae adapt to warmer water, and new ecological relationships form in disturbed environments. Evolution does not pause, it redirects. Already some bacteria have been found metabolizing synthetic polymers, converting human waste into energy. These microbes are the pioneers of a new biochemical era. They are the beginning of a future fossil record that includes not just our materials, but the life forms that evolved to consume them. The creatures that will inherit our ocean may look familiar but behave differently. Species that thrive in variable conditions, jellyfish, certain algae, hardy crustaceans, are already expanding their range. Coral reefs may shrink but will not vanish entirely. Some will shift poleward as temperatures rise. New symbioses will emerge, replacing those that fail. The fossil record of the future will not be a story of collapse alone, but of transition, a layer of loss followed by one of renewal, as has been many times before. From the planet's perspective, mass extinctions are corrections, not endings. Each one resets complexity and rewrites diversity. The Permian, the Cretaceous and the Paleocene all saw enormous loss followed by new invention. If humanity's impact triggers another such shift, the ocean will archive it as it did the rest, indifferently, thoroughly and accurately. It will take the debris of cities, the bones of whales tangled in nets, the particles of microplastic and glass, and press them together into stone. Millions of years from now, layers of compressed sand and polymer may lie beneath what's left of continents, marking our existence more clearly than any monument or digital record could. Our fossils, when they appear, will not be elegant. They will not resemble the delicate shells of ammonites or the spirals of coral. They will be mixtures, concrete fused with shell fragments, metal corroded into oxide seams, ceramic particles mixed with organic remains. A geologist of the far future might find a layer rich with silica glass, aluminum alloys, and microplastic spheres, and infer that a strange, brief civilization covered the Earth, reshaping it and then vanishing abruptly. The evidence will be undeniable even if the meaning is lost. In this sense, we have already become part of the ocean's deep memory. Every ship that sinks, every cable laid, every city runoff that reaches the sea is an entry in that record. The ocean is patient. It doesn't judge, it collects. Over time, currents will distribute our legacy evenly, sorting it by density and grain, embedding it in sediment. The process is impartial and inevitable. Human traces will become part of the same archive that holds trilobites, ammonites, and coral reefs. The continuity will be seamless. The idea of future fossils invites a kind of humility. We often think of ourselves as observers of nature, not participants. But the ocean has absorbed us completely, chemically and physically. Even our absence will leave a shape in its layers. Our technology, our waste, our inventions, and new forms of mineralization. We're no longer separate from geology. We are part of it. The Anthropocene will end one day, not through resolution but through integration. When the ocean eventually recovers its equilibrium long after our species has diminished or changed, the materials we made will remain. Plastics will degrade into waxy residues embedded in rock. Metals will oxidize into thin seams. Radioisotopes will decay to stable forms, leaving faint traces of their presence. To any future intelligence that examines these remnants, it will be clear that something once lived here that mastered transformation. A species capable of rearranging the planet's chemistry in a geological instant. Even the data we store, magnetic patterns on drives, binary signals transmitted through fiber optics beneath the sea, may leave microscopic changes. Cables and conduits stretching across the seabed will fossilize into long metallic veins. The patterns of our communication infrastructure will become trace fossils of thought, etched in mineral and sediment. The ocean will preserve not only what we built, but how we connected. There's an irony in it. The same ocean that erased the traces of entire continents' worth of civilizations through erosion and plate movement will keep ours intact, at least chemically. Our durability ensures our disappearance will be visible longer than our presence ever was. The reef-building corals wrote their story in stone by growing. We have written ours by discarding. Both methods leave evidence. Both become part of the same clock the ocean keeps. In the end, the distinction between natural and artificial fades. The ocean doesn't classify, it absorbs. Whether a shell or a bottle cap, a bone or a circuit board, everything becomes sediment eventually. Over time, the difference between organic and synthetic diminishes as molecules rearrange. The deep sea doesn't distinguish intention, it only records composition. That is the ultimate equality. Every trace reduced to matter, every story compressed into geology. And so, the next layer of the ocean's archive is forming quietly as we live. It thickens beneath shipping lanes, beneath deltas, beneath melting ice. It mixes with volcanic ash, pollen, and the remains of plankton. The process is slow but certain. Someday, far beyond our lifespan, the ocean will close over it entirely, sealing our chapter beneath kilometers of sediment. The pressure will compact it, the chemistry will fuse it, and what remains will be as permanent as any fossil ever found. Above this slow recording, life continues. Fish still migrate. Whales still sing, their voices distorted but not silenced. Coral larvae still drift, seeking new foundations. The ocean absorbs our noise but continues its rhythm. Even as it changes, it preserves continuity. The future fossils will not only tell what was lost but what endured. They will show that after every disturbance, life resumed its work of building, filtering, drifting and waiting. The continuity will be imperfect, but it will be there. The sea, as always, will turn everything, movement, waste, death, creation, into equilibrium. It will turn us into memory, not myth. And as the tides erase the surface evidence of our civilization, the deep will keep its record intact, storing our brief existence in the same calm patience with which it has stored all of history. And somewhere in that slow layering, amid the particles of plastic and bone, between the shells of dead plankton and the rust of machines, there will be traces of the ancient creatures that still endure. The nautilus, the coral, the crab, the jellyfish. Their presence will outlast ours, as it always has. The ocean's memory will blend us together. Our time will be another sedimented moment, one more page in the long chronicle of endurance. And as that chronicle continues to build, something even more ancient will keep writing. not through motion or invention, but through the same slow persistence that began before there were even shells or skeletons to preserve. The ocean remembers everything, and in its depths, remembrance is survival. It continues not through creation, but through the act of never forgetting. The ocean has no beginning that we can name. It existed before the continents took shape, before the air was breathable, before the sun's warmth could penetrate more than a few meters beneath the waves. It has changed colour, chemistry, and life countless times. But it has never stopped being itself. Every molecule of water on the planet has been through millions of transformations, evaporated, condensed, frozen, melted, consumed, expelled, cycled through countless bodies and rocks and clouds. The ocean is the sum of all those transformations, the physical memory of the Earth. It doesn't record events in words or symbols. It records through matter, through motion, through the constant rearrangement of elements that once belonged to everything that has ever lived. Every time rain falls, it carries with it atoms once part of living cells. Every drop that flows into the sea adds a fraction of history. In that sense, the ocean is not just the archive of life, but its bloodstream, circulating the materials of the dead into the bodies of the living. Coral reefs are made of calcium from ancient shells. The plankton that drift in the current contain phosphorus from bones, nitrogen from decomposed flesh, and carbon once locked in fossilized plants. The water that laps against the shore is not new. It's endlessly recycled memory, rearranged by wind and gravity. When we look out across the surface, we see motion, waves, reflections, foam. But underneath that restlessness is a kind of still memory that extends across time. It's in the sediment that collects grain by grain at the bottom of trenches. It's in the chemistry of shells and skeletons. It's in the DNA of creatures that have changed little since the first multicellular life emerged. To say that the ocean remembers is not metaphor, it's description. Every physical process within it carries information about what has been. The oldest sediments on Earth lie beneath the sea. They preserve traces of ancient atmospheres, microbial films and volcanic eruptions. Each layer, thin as paper but stretching for kilometers, is a record of conditions that shaped the evolution of life. Scientists can read these layers the way one reads pages, reconstructing climate, temperature, and biodiversity millions of years old. Even the simplest fossilized ripple on stone tells a story of motion captured and preserved by time. The ocean does not keep memory in order. It stores it as accumulation, one layer over another, until the record becomes the world itself. Every organism that has ever lived in the sea has contributed to this record. The shells of plankton, the skeletons of corals, the scales of fish, the cartilage of sharks, all fall, dissolve, and settle. Over eons they form limestone, chalk, and shale. Mountains that rise on land today began as sedimentary beds under ancient oceans. The peaks that pierce clouds once lay beneath waves, collecting shells and bones. When we stand on a mountain ridge and see fossils embedded in rock, we're looking at the ocean's memory lifted into the sky. The planet constantly recycles its own past, turning the seabed into landscape and then back into sea again. Even the elements of life's chemistry reflect this continuity. The sodium in our blood, the chloride that balances our cells, the calcium in our bones, all come from the ocean. They are remnants of a time when our earliest ancestors were single cells drifting in salt water. Our internal fluids still carry roughly the same ratio of salts as seawater does. In a literal way, we are walking extensions of the ocean's chemistry. The memory of the sea is written in our bodies. The creatures that continue to live there embody that memory directly. The horseshoe crab, the nautilus, the kilacanth, the jellyfish, all of them are living fragments of ancient eras. Their bodies are blueprints from before vertebrates dominated, before land was green, before time itself had the scale we now imagine. They persist not as relics, but as proof of the ocean's ability to preserve what works. Their presence connects every era in a single living chain. When they move, they repeat gestures made millions of years ago. Memory in the ocean isn't sentimental, it's functional. It remembers what endures. Each extinction event has erased species but refined the balance of chemistry and flow that allows life to re-emerge. The oxygen cycles, the carbon exchange, the migration of nutrients from surface to deep, all continue regardless of what forms occupy them. In this sense, the ocean remembers not individuals but relationships, predator and prey, reef and current, light and darkness, surface and abyss. Those relationships are constants, redefined with each generation of life but never lost. To the ocean, time and memory are inseparable. Sediment accumulates as time passes. Chemical gradients change slowly, marking epochs. The circulation of deep water, the thermohaline conveyor, takes 1,000 years to complete one loop around the globe. Each molecule of water carries a signature of where it has been. The cold of polar seas, the warmth of equatorial shallows, the minerals of the continental shelf. The ocean remembers geography the way we remember emotion, not as fixed images but as flows that define identity. Even the ocean's currents carry history. The Gulf Stream, for example, has been flowing in some form for millions of years, shaping climate and evolution on land. Its temperature and salinity variations tell the story of ice ages and interglacial periods. The Antarctic Circumpolar Current, the largest on Earth, connects all major oceans and distributes nutrients across hemispheres. Its strength records the isolation of Antarctica, the cooling of the planet, the establishment of the modern climate system. Each current is a moving archive, preserving memory through motion rather than sediment. The creatures within those currents also serve as record keepers. Migrating whales travel routes that echo paths carved by their ancestors for generations. Turtles return to beaches where their species first nested thousands of years ago. Fish spawn in cycles synchronized with the lunar calendar, a rhythm older than the continents themselves. These patterns are biological memory, instincts coded through evolution. The ocean doesn't forget the way migration feels. It passes the knowledge through DNA and behavior. Every journey repeated is another act of remembrance. Human beings, despite our separation by cities and continents, are drawn instinctively to this memory. Standing at the shore, watching waves break, we are witnessing the oldest continuous process on the planet. The sound of surf, constant and unchanging, is the ocean's language of recall. It's the sound of energy transferred from wind to water, from distant storms to local beaches across thousands of miles. Each wave is a pulse of time. Each crest carries particles from every corner of the world, molecules that have been part of countless bodies and forms. When we breathe the salt air, we inhale the history of everything that has ever touched the sea. This sense of connection has shaped cultures as much as it has shaped biology. Myths of creation often begin with water because water precedes everything else. Civilizations have treated the sea as both boundary and origin, as mystery and mirror. Yet beneath those symbolic interpretations lies a physical truth. The ocean sustains continuity. It outlasts language, religion and empire. It erases and rebuilds coastlines, renews climates, and redistributes life. The memory of humanity will one day be part of its sediment, but the ocean itself will continue, altered but unbroken. The resilience of this system depends on balance. When chemistry shifts too far, too much carbon, too little oxygen, the ocean resets through feedback. Algae bloom, species migrate, deep currents adjust. It is not conscious correction, but natural physics seeking equilibrium. Every disruption becomes a future memory, encoded as a layer of difference. The ocean's stability arises from its capacity to absorb change, to turn events into record. Nothing is lost, only transformed. In that way, even destruction becomes part of continuity. Coral bleaching, mass die-offs, plastic pollution. These are not endings, but new data in the ocean's record. Life responds, adapts, or evolves around them. The microbial world rewrites metabolism to digest what didn't exist before. The larger organisms shift range, diet, or form. The system absorbs and continues. To remember everything is not to remain unchanged. It's to change without losing history. When viewed across geological time, the ocean's patience becomes almost beyond comprehension. It has witnessed every possible experiment life could make. Creatures that flew underwater, plants that turned into animals, animals that turned back into plants, species that used light, heat, or pressure as tools. It has hosted extinction and invention in endless repetition. The fact that it still supports life after billions of years means that its memory functions as guidance. Every adaptation that works becomes a template. Every failure becomes sediment. The next forms that rise from the sea will carry traces of all that came before. The ocean doesn't separate past from present. To it, everything that has ever lived still exists in some form, as molecules, as influence, as structure. The limestone cliffs made from coral reefs, the chalk deposits formed by plankton shells, the oil beneath seabeds created from ancient algae. These are all memories turned into resource, remnants turned into energy. The cycle is complete and continuous. The sea reuses its own past perpetually, and while the land erodes and continents drift, the ocean maintains its depth as a constant field of renewal. It's the one environment that has persisted across all ages. The atmosphere has changed composition dozens of times. The ocean has remained liquid. It has frozen, thawed, expanded, contracted, but it has always been there, always recording, always holding. In that constancy lies the foundation of every evolutionary success. Life's durability comes from being born in something that remembers. The same process that stores history also erases it from immediate sight. Sediment buries wrecks, coral overgrows ruins, currents scatter remains. The ocean hides its memory by preserving it. What disappears to us is not forgotten. It's simply filed away in deeper layers. Ancient shipwrecks turn into reefs, iron hulls become home for fish, and bones sink into ooze that one day becomes rock. The boundary between memory and function dissolves. Everything becomes useful again. When future scientists, whoever they are, study these records, they will find no gaps. The ocean does not skip chapters. It records even the smallest events, a volcanic eruption, a sudden shift in plankton, a century of human industry, and integrates them into the whole. It doesn't care for meaning, it cares for detail. Each particle, each chemical trace, is a piece of an unbroken continuity that stretches back to the planet's formation. To imagine the ocean remembering is to recognize that memory itself may not need consciousness. It may only need persistence. The sea's persistence is perfect. It forgets nothing because it cannot. Its entire existence is an act of retention, every molecule capable of transformation but not loss. Water cycles through forms, vapour, liquid, ice, but never leaves the system. The memory of the ocean is the planet's way of ensuring that nothing truly ends. And so, even as we change it, even as our species adds new layers to its archive, the ocean continues its task without judgment. It folds our actions into its depth, processing them as it has processed everything. One day, our ruins will dissolve, our materials will settle, and the sea will close over them completely. The balance will shift again. New forms will arise and the cycle will continue. The ocean's memory will hold both our presence and our absence with the same calm precision. Somewhere, deep beneath where sunlight dies, microbial mats will continue to photosynthesize from faint chemical gradients. Corals will rebuild from fragments. Sharks will glide through water the way they did before we existed. The whales, or whatever comes after them, will still move with the rhythm of the planet's rotation. The sediment will thicken, the current will flow, and through it all, The ocean will remember. It will remember not through thought but through matter, not through stories but through continuity. It will remember the first bacteria that split water molecules, the trilobites that crawled across the sea floor, the ammonites that spiraled through Mesozoic tides, the fish that learned to breathe air, the mammals that returned to the sea, and the humans who measured and mapped and briefly believed they understood it. All of them will remain within its chemistry. None of them will truly vanish. In the end, the ocean is not a witness to history. It is history. It is everything that has ever happened on this planet, suspended in solution, carried in currents, crystallized in rock. Every drop holds memory, and every wave erases only what the surface needs to forget. Beneath that surface, nothing is lost. The deep remains unchanged in its purpose, the vast, slow mind of the planet, remembering everything